You are listening to the Developer's Guide to RabbitMQ, Building Robust Message-Driven Systems. Like and subscribe to keep up to date on our latest audiobooks. The Developer's Guide to RabbitMQ, Building Robust Message-Driven Systems. Chapter 1, The World of Message Queues and Why RabbitMQ. 1.1 Introduction. The Challenge of Modern Applications. In the early days of software development, many applications were built as large, single, self-contained units known as monoliths. Picture a sprawling mansion where everything, the kitchen, bedrooms, living room, and even the plumbing and electricity, is all part of one massive structure. While this approach can be simpler to start with, it quickly presents challenges as the system grows. Imagine that mansion needs a new, faster kitchen. To upgrade it, you might need to shut down the entire house, causing disruption to everyone. If one part of the house, say the electrical system, fails, the entire mansion could go dark. Scaling such a system, meaning making it capable of handling more users or more complex tasks, often means scaling the entire mansion, even if only one room is experiencing heavy traffic, leading to inefficient resource use. Deploying updates becomes a nerve-wracking affair, as a single bug in one room could bring down the whole house. Modern software, especially in the era of cloud computing, microservices, and distributed systems, demands a different approach. Applications are no longer single-piece monoliths, but often a collection of smaller, independent services, each responsible for a specific function. Think of a city where each building, service, has its own purpose: a post office, a fire station, a library, and they communicate with each other. This distributed architecture addresses many of the monolithic challenges, but it introduces its own set of complexities. How do these independent services talk to each other reliably? How do they handle periods of high demand without crumbling? How can one service fail without bringing down the entire city? This brings us to the critical need for scalability, resilience, and decoupling. Scalability means the ability of a system to cope with increased workload. Can your application handle 5 users, 500, or 5 million efficiently and without re-architecting everything? Resilience refers to a system's ability to recover from failures and maintain functionality. If one service in your distributed system crashes, does the whole system break, or can it continue operating smoothly? Decoupling is about reducing interdependencies between components. If your order processing system doesn't need to know the intimate details of how the payment processing system works, you can update one without necessarily affecting the other. This grants flexibility and reduces the blast radius of changes or failures. Achieving these 3 pillars is fundamental to building robust, modern applications. And this is precisely where message queues, and specifically RabbitMQ, come into play. 1.2 Understanding synchronous versus asynchronous communication. To truly appreciate the value of message queues, it's essential to understand the distinction between synchronous and asynchronous communication paradigms. Consider the classic example of ordering food at a restaurant. Synchronous communication, the patient waiter. Imagine you're at a busy restaurant. In a synchronous system, the waiter takes your order, then waits right there until the chef cooks your meal, brings it out, and you finish eating before moving on to the next table. If the kitchen is slow, or if there's a problem with your order, the waiter is stuck, unable to serve any other customers. This is highly inefficient in a busy environment. In software terms, a client makes a request to a server, and then blocks or waits for the server to process the request and send back a response before doing anything else. If the server is busy, slow, or crashes, the client is left waiting indefinitely or times out, potentially hindering other operations. Asynchronous communication, the efficient waiter. Now consider an asynchronous system at the same restaurant. The waiter takes your order, passes it to the kitchen, and immediately moves on to serve other tables. The kitchen operates independently, processing orders as they come in. When your meal is ready, it's delivered to your table. The waiter, independent of the kitchen's cooking time, maximizes their efficiency. In software, this means a service can send a message or task to another service and immediately continue with its own work, without waiting for an immediate response. The receiving service picks up the message when it's ready, processes it, and might send back a response later, if necessary. Benefits of asynchronous communication, non-blocking operations. Senders are not blocked waiting for receivers, improving overall system responsiveness. Increased throughput. Systems can handle more requests in parallel. Better resource utilization. Resources aren't tied up waiting. Resilience. If the receiver is temporarily unavailable, messages can be stored and processed once it's back online, preventing data loss and service interruption for the sender. Decoupling. Senders don't need to know if the receiver is up, what its IP address is, or how it processes the message. They just need to know where to send the message. While asynchronous communication introduces some complexity, particularly around ensuring messages are successfully processed and managing eventual consistency rather than immediate consistency, its benefits are paramount for building systems that are truly scalable, resilient, and decoupled. 1.3. Introducing message queues. At the heart of asynchronous communication in distributed systems lies the concept of a message queue. So, what is a message queue? At its simplest, it's a buffer for messages. Think of it as a specialized inbox or a holding area where software applications can send messages to each other without having to be available at the same time. Here's how it generally works. A producer, an application or service, creates a message and sends it to the message queue. The message queue stores the message. A consumer, another application or service, connects to the message queue and retrieves messages for processing. The message queue acts as an intermediary, facilitating communication between different parts of a system. This simple mechanism unlocks powerful advantages. Decoupling. Producers and consumers don't need to know about each other's existence or location. They only need to know how to interact with the message queue. This means you can change, upgrade, or even rewrite a producer or consumer service without affecting the other, as long as they adhere to the agreed-upon message format. Load leveling or throttling. Imagine your e-commerce website experiences a sudden surge in orders during a flash sale. Instead of direct communication that could overwhelm your order processing service, all new orders are first sent to a message queue. The order processing service then pulls messages from the queue at a rate it can comfortably handle, even if the incoming rate is much higher. This prevents your backend from crashing under heavy load and allows it to process all orders eventually. Resilience and durability. If a consumer service goes down, messages aren't lost. They remain in the queue until the service recovers and can pick them up. If the message queue itself is configured for durability, messages can even survive a restart of the message queue broker. This means your data is safe, and your system can tolerate temporary outages in its components. Scalability. You can easily add more consumers to process messages from a queue in parallel, distributing the workload and increasing throughput. Conversely, if demand drops, you can scale down consumers to save resources. To provide a real-world perspective, consider how a large tech company might use message queues. When a user uploads a new profile picture, that action kicks off a cascade of events. The image needs to be resized to various dimensions for different devices, watermarked, analyzed for content, and stored in multiple locations. Instead of the upload service trying to directly call all these other services in sequence, which would be slow and prone to failure, the upload service simply publishes a new image uploaded message to a message queue. Dedicated services for resizing, watermarking, analyzing, and storing all subscribe to or consume from this queue. If the image analysis service is busy, the message just waits in its queue until it's ready. This significantly improves resilience, allows for independent scaling of each task, and reduces latency for the initial upload. 1.4 Why RabbitMQ? While the concept of message queues is broad, RabbitMQ is a specialized piece of software, known as a message broker, that implements this concept. Among the various message brokers available today, like Apache Kafka, ActiveMQ, or Amazon SQS, RabbitMQ has carved out a significant niche. 1.4.1 A brief history and community strength. RabbitMQ started in 2007 and was acquired by Pivotal, now part of VMware, in 2013. It is open source, written in Erlang, and has a mature, active, and vibrant community. This means ongoing development, robust support, and a wealth of existing documentation and examples. Its maturity speaks to its stability and reliability in production environments across thousands of organizations. 1.4.2 Adherence to AMQP standard. A critical differentiator for RabbitMQ is its primary implementation of the Advanced Message Queuing Protocol, AMQP. AMQP is an open, standardized protocol for message-oriented middleware. This adherence to an open standard means you are not locked into a proprietary system. It specifies the rules for how message brokers and clients should interact, ensuring interoperability. While RabbitMQ supports other protocols like MQTT and Stomp, AMQP is its native tongue, offering powerful and flexible routing capabilities. 1.4.3 Feature Set Overview. RabbitMQ provides a rich set of features that make it a compelling choice for developers. Flexible routing. Beyond simple point-to-point queues, RabbitMQ offers powerful routing capabilities through exchanges. You can send messages to multiple queues simultaneously, route messages based on patterns, and much more. Reliability and persistence. It offers mechanisms to ensure messages are not lost, even if the broker crashes or if consumers fail during processing. This includes message acknowledgements, durable queues, and publisher confirms. Rich client libraries. Given its popularity, RabbitMQ has excellent client libraries available for nearly every major programming language, including Python, Java, Net, Node.js, Go, PHP, and Ruby. This makes integration straightforward for diverse technology stacks. Management and monitoring. It comes with a robust web-based management, user interface, and command line tools to monitor, configure, and troubleshoot your RabbitMQ instances. Clustering. For high availability and increased throughput, RabbitMQ can be run in a clustered configuration, distributing queues and messages across multiple nodes. 1.4.4 When to choose RabbitMQ and when not to. RabbitMQ excels in scenarios where you need complex routing, when messages need to be routed based on specific criteria to different consumers or broadcast to many. Guaranteed message delivery, for critical tasks where message loss is unacceptable. Asynchronous processing, long-running tasks, notifications, event-driven architectures. Loose coupling, breaking down monolithic applications into microservices. A mature and battle-tested solution, backed by an active community and used extensively in production. While RabbitMQ is versatile, it might not be the top choice for use cases that require massive, raw throughput for streaming very large volumes of data, e.g., millions of messages per second in real-time sensor data aggregation. For such scenarios, technologies like Apache Kafka, designed as a distributed streaming platform, might be more appropriate. However, for most general-purpose message queuing, task processing, and inter-service communication needs in application development, RabbitMQ is a superb and robust choice. 1.5 Setting Expectations. What you'll learn. This book is your practical guide to understanding, implementing, and mastering RabbitMQ for building robust, scalable, and resilient distributed applications. By the end of this journey, you will grasp the fundamental concepts of message queues and asynchronous communication. Understand the core architecture of RabbitMQ, including exchanges, queues, and bindings. Be able to install and set up your own RabbitMQ environment. Write applications that produce and consume messages using various patterns, like work queues, publish, subscribe, and routing. Implement critical features for reliability, such as message acknowledgements, durability, and handling unprocessable messages. Learn how to monitor and manage your RabbitMQ instances effectively. Discover common architectural patterns and best practices for deploying RabbitMQ in production. Whether you're developing microservices, building event-driven systems, or simply seeking to improve the resilience and scalability of your applications, RabbitMQ offers a powerful solution. Let's dive in and unlock its potential. Chapter 2, Deciphering RabbitMQ, Core Concepts Explained. In Chapter 1, we explored the why behind message queues and asynchronous communication, positioning RabbitMQ as a powerful tool in a developer's arsenal. Now, it's time to delve into the what and how of RabbitMQ. Like any complex system, Understanding RabbitMQ requires familiarizing yourself with its fundamental building blocks and the relationships between them. These components orchestrate the flow of messages, ensuring they get from their origin to their intended destination efficiently and reliably. Imagine RabbitMQ not just as a single entity, but as a sophisticated post office with specialized roles and processes. We'll use this analogy frequently to help clarify the concepts. 2.1 Introduction to RabbitMQ's anatomy. At the highest level, RabbitMQ is a message broker. It's the central nervous system that facilitates communication between different applications without them needing to know each other's precise location or availability. 2.1.1 The broker. The heart of RabbitMQ. The broker itself is the RabbitMQ server instance you install and run. It's the engine that powers the entire messaging system. All messages flow through this broker. When we talk about RabbitMQ, we're generally referring to this broker and the services it performs. It's responsible for receiving messages from senders, routing them, storing them, and delivering them to receivers. Think of the broker as the entire post office building itself, housing all the operations. 2.1.2 Virtual hosts. Logical isolation. Within a single RabbitMQ broker, you can create multiple virtual hosts, often abbreviated as vhosts. A virtual host provides a way to logically group related exchanges, queues, and permissions. It acts like a separate, isolated environment within the same RabbitMQ instance. Why would you use them? Imagine you have two different applications, perhaps one for your e-commerce platform and another for your internal HR system. Both need to use RabbitMQ, but you want to keep their messages, queues, and configurations separate to avoid conflicts and increase security. By assigning each application its own virtual host, they operate independently, as if they were on separate RabbitMQ servers, even though they share the same physical broker. This prevents an application from accidentally or maliciously interfering with another's messaging structure. You can set permissions for users on a per virtual host basis. For instance, a user might have full access to /ecommerce but no access to /HR. By default, RabbitMQ creates a /virtual host, often called the root or default vhost. While convenient for quick experimentation, it's a best practice to create named virtual hosts for your actual applications. 2.2 Messages. The units of communication. At its essence, RabbitMQ is about moving messages. A message is the actual data that's being transferred from one application to another. 2.2.1 Message body and properties. Every message has two main parts, body, payload. This is the actual data you want to send. It could be a JSON string representing an order, a binary image, a log entry, or any other piece of information. RabbitMQ treats this as an opaque byte array. It doesn't try to understand the content. It's your responsibility to ensure the producer and consumer agree on the format, e.g., JSON, XML, protocol buffers. Properties. These are metadata about the message itself, rather than the content. They can include things like a content type, e.g., application/JSON, content encoding, e.g., UTF-8, message ID, correlation ID, useful for tracking request-response patterns, reply to queue, and even custom headers. Properties are crucial because they allow the broker and consumers to make intelligent decisions about how to handle the message without needing to inspect its body. For example, a content type property tells the consumer how to decode the message body correctly. 2.2.2 Routing key and its importance. One of the most vital properties of a message is its routing key. When a producer sends a message to RabbitMQ, it publishes it with a routing key. This string acts like an address or a category label for the message. However, the message isn't sent directly to a queue using this key. Instead, as we'll see shortly, the routing key is used by an exchange to determine which queues the message should be delivered to. The format and significance of the routing key depend entirely on the type of exchange to which the message is sent. 2.3 Producers. Sending the message. A producer is any application or service that sends messages to a RabbitMQ broker. From the producer's perspective, the process is straightforward. It creates a message with a body and properties and then publishes it. When a producer publishes a message, it doesn't send it directly to a queue. This is a critical distinction in RabbitMQ. Instead, the producer sends the message to an exchange. Think of it like dropping a letter into a mailbox. You don't put it directly into the postman's bag or a specific recipient's mailbox. You drop it into a general collection point. The producer's job is simply to generate and dispatch the message. It doesn't care, and shouldn't care, how the message ultimately gets routed to a queue or how many consumers process it. This separation of concerns is a fundamental aspect of RabbitMQ's powerful decoupling capabilities. 2.4 Exchanges, the message routers. If a producer is like someone dropping a letter into a mailbox, then an exchange is the post office's central sorting desk. The exchange receives messages from producers, and based on its type and the message's routing key, decides which queues, if any, it should deliver the message to. This is where the magic of RabbitMQ's flexible routing happens. There are several types of exchanges, each with a different routing algorithm. 2.4.2.1 Direct Exchange. Exact match routing. A direct exchange delivers messages to queues whose binding key exactly matches the message's routing key. It's like mailing a letter that specifies, deliver to QA, if a queue is bound to a direct exchange with the binding key, QA, and a message arrives at that exchange with the routing key, QA, the message will be delivered to that queue. If no queue has a matching binding key, the message is discarded. Analogy: a direct instruction to deliver specific mail to a specific mail slot. 2.4.2.2 Fanout Exchange. Broadcast messaging. A fanout exchange is the simplest and least selective. It broadcasts all messages it receives to all queues that are bound to it, regardless of the message's routing key. The routing key, in this case, is completely ignored. Analogy: like broadcasting an announcement over a loudspeaker. Everyone who is listening, i.e., whose queue is bound to this exchange, receives a copy of the message. This pattern is ideal for publish-subscribe scenarios, where multiple consumers need to receive the same message, e.g., a new product added event needs to be consumed by the search indexer, inventory manager, and marketing campaign planner. 2.4.2.3 Topic Exchange. Pattern-based routing. A topic exchange provides pattern-based routing, making it highly flexible. Messages are routed to queues based on a pattern match between the message's routing key and the binding key of the queue. The routing keys and binding keys are typically structured as a list of words delimited by dots, e.g., stock dot, ust nysc by. Binding keys can include two special characters. Asterisk matches exactly one word. Hash matches 0 or more words. Example: if a queue is bound with the binding key stock.ust hash, it will receive messages with routing keys like stock.ust nysc by, stock.ust london cell large, but not stock.ur nysc by. Analogy: subscribing to news categories. You might subscribe to sports notices from US, current year, sports.us hash, and get all sports news from the US regardless of the specific sport or year. 2.4.2.4 Headers Exchange. Briefly mention. A headers exchange routes messages based on the message headers, rather than the routing key. It matches messages where the header properties either match all match, or any match of the binding arguments. While powerful for specific use cases, they are less commonly used than direct, fanout, or topic exchanges for general message routing. 2.5 Queues. Where messages reside. If exchanges are the sorting desks, then the queue is the literal mailbox, or waiting line for messages. A queue is the basic storage buffer where messages wait until they are consumed by an application. Messages are consumed from the front of the queue, typically in a first-in, first-out FIFO manner. 2.5.1 What is a queue? Queues have names, e.g., order processing queue, email notification queue. Producers don't know or care about these names directly. They simply publish to an exchange. It's the exchange's job to route the message to the correct queues based on its bindings. 2.5.2 Queue Naming and Properties. When you declare a queue, you can specify several important properties. Durable. A durable queue will survive a RabbitMQ server restart. If the server goes down, the queue and messages within it, if they are also marked as durable, will be recovered when the server comes back online. This is crucial for reliability. For non-durable queues, they are deleted when RabbitMQ shuts down. Exclusive. An exclusive queue can only be accessed by the current connection and is deleted when that connection closes. This is useful for temporary client-specific queues. Auto-delete. An auto-delete queue is removed automatically when the last consumer disconnects from it. This is handy for temporary queues used in scenarios like request-response patterns, where the queue is only needed as long as the consumer is active. Choosing these properties wisely depends on your application's requirements for persistence and queue lifecycle. 2.6 Consumers. Receiving and processing messages. A consumer is any application or service that connects to RabbitMQ to retrieve and process messages from a queue. Consumers typically listen for messages on a specific queue. When a new message arrives in that queue, RabbitMQ delivers it to one of the connected consumers. 2.6.1 What is a consumer? Consumers are the workers in our distributed system. They are responsible for the business logic associated with a message. For instance, an order processor consumer might pull new order messages, validate them, and update a database. An email sender consumer would receive, send email messages, and trigger an email delivery service. 2.6.2 How consumers connect to queues. Consumers establish a connection to the RabbitMQ broker and then declare their interest in consuming messages from a specific queue. RabbitMQ then pushes messages to the consumer. The consumer typically processes the message and then sends an acknowledgement back to RabbitMQ, indicating that the message was successfully processed and can be safely removed from the queue. This acknowledgement mechanism is vital for building reliable systems, which we will explore in more detail in Chapter 6, 2.7 Bindings. Connecting exchanges to queues. We've talked about producers sending messages to exchanges and exchanges routing messages to queues, where consumers pick them up. The missing piece in this puzzle is how an exchange knows which specific queues to send messages to. This is where bindings come in. A binding is a rule or a relationship that tells an exchange to send messages to a specific queue. It's simply a connection between an exchange and a queue, optionally defined with a binding key. Think of it like this: exchange, the sorting desk; queue, a specific mailbox. Binding. A sign on the sorting desk that says, any mail with routing key X should go to mailbox Y. 2.7.1 The rules of routing. The routing behavior depends entirely on the exchange type. Direct exchange. A binding specifies a binding key. Messages arrive at the exchange with a routing key. If the message's routing key exactly matches the binding key, the message is sent to the bound queue. Fan-out exchange. Bindings don't use a binding key. Any queue bound to a fan-out exchange will receive all messages sent to that exchange. The binding simply establishes a connection. Topic exchange. Bindings define a pattern, the binding key, using and messages with routing keys matching that pattern will be sent to the bound queue. 2.7.2 Binding keys versus routing keys. It's crucial not to confuse binding keys with routing keys. Routing key. This is part of the message, set by the producer, and helps the exchange decide where to send the message. Binding key. This is part of the binding, set during setup, and tells the exchange what messages it is interested in for a particular queue. They work in conjunction. The exchange evaluates the message's routing key against the binding keys of all its connected queues to determine where to deliver the message. 2.8 Putting it all together. A mental model. Let's synthesize these concepts with our post office analogy. Producer, you write a message, letter, with a routing key, destination, address like urgent airmail Paris. You drop your message into a general exchange, the post office mailbox sorting desk. The exchange, post office sorting desk, receives your letter. Based on its type, e.g., an international airmail exchange, which is a topic exchange, and your letter's routing key, it looks at its internal bindings, rules for mail distribution. If there's a binding that says, any airmail for urgent airmail should go to the urgent mail in Paris queue, your letter is routed to that queue. The queue, a specific mailbag or slot for urgent mail in Paris, holds your letter until it's picked up. The consumer, a postal worker assigned to the urgent mail in Paris, mailbag, retrieves your letter from the queue and processes it, delivers it. It's important to note that a single message can be routed to multiple queues, e.g., via a fan-out exchange or multiple bindings on a topic direct exchange, and multiple producers can send messages to the same exchange, which can then route them to the same or different queues. Similarly, multiple consumers can process messages from the same queue, allowing for work distribution. 2.9 Summary of Core Components. You now have a foundational understanding of the key components that make RabbitMQ function. Broker, the central RabbitMQ server managing all messaging operations. Virtual hosts, vHosts, isolated environments within the broker for logical separation of resources. Messages, the data units being transmitted, comprising a body and properties like the routing key. Producers, applications that create and publish messages to exchanges. Exchanges, message routers that receive messages from producers and distribute them to queues based on their type, direct, fan-out, topic, headers, and routing binding keys. Queues, buffers that store messages until they are consumed. They can be configured with properties like durability, exclusivity, and auto-deletion. Consumers, applications that retrieve and process messages from queues. Bindings, the rules that connect exchanges to queues, often with a binding key that specifies the routing criteria. With these core concepts firmly in mind, you have a solid conceptual framework for how messages flow through RabbitMQ. In the next chapter, we'll shift from theory to practice and get RabbitMQ up and running on your development machine, taking the first steps towards building your own message-driven applications. Chapter 3. Getting Started. Installation and First Steps. With a clear understanding of RabbitMQ's core concepts from Chapter 2, it's time to roll up our sleeves and get our hands dirty. This chapter will guide you through setting up a RabbitMQ environment on your local machine, introduce you to its essential management interface, and walk you through sending and receiving your very first messages. 3.1 Introduction. Setting up your RabbitMQ environment. To begin working with RabbitMQ, you need a running instance of the broker. While there are various ways to install RabbitMQ, for developers, the most efficient and recommended approach for local development is using Docker. Docker provides a consistent, isolated environment, meaning you won't encounter "it works on my machine" issues due to conflicting dependencies or system configurations. 3.2 Prerequisites. Docker and your favorite language. Before we proceed, ensure you have Docker Desktop. This includes the Docker Engine, CLI client, Docker Compose, Kubernetes, and the Graphical User Interface (GUI) app. You can download it from the official Docker website for Windows, macOS, or Linux. Verify your installation by opening a terminal or command prompt and typing Docker version. You should see output indicating the Docker version. A text editor or IDE, such as Visual Studio Code, IntelliJ IDEA, PyCharm, etc. Your preferred programming language runtime. While we won't dive into specific code examples in this chapter, having your language environment set up will be useful for later chapters when we implement producers and consumers. Common choices include Python, Node.js, Java, C, Go, and PHP. 3.3 Installing RabbitMQ. 3.3.1 Using Docker. Recommended for local development. Docker offers the simplest and most consistent way to get RabbitMQ running for development and testing. Step 1. Open your terminal. Launch your terminal Mac OS Linux or Command Prompt PowerShell Windows. Step 2. Run the RabbitMQ Docker image. Execute the following command. Docker run it rm name RabbitMQ, P5672 5672, P15672 15672 RabbitMQ. 3. Management. Let's break down this command section by section so you understand what's happening. Docker run. This is the base command to create and run a container from a Docker image. This combination keeps the terminal attached, I for interactive, and allocates a sudo tty, allowing you to see the container's logs and interact with it, though we won't actively type into it. rm. This is a very useful flag for development. It tells Docker to automatically remove the container and its file system when the container exits. This prevents your Docker system from accumulating many stopped containers from quick tests. Be aware, any data, like messages stored in queues, will be lost when the container stops if you use this flag. For production or persistent development, you'd typically manage volumes separately. Name RabbitMQ. This assigns a human-readable name, RabbitMQ, to your container. This makes it easier to refer to this specific container in other Docker commands, e.g., docker stop RabbitMQ. P5672-5672. This performs port mapping. The first 5672 is the port on your host machine, your computer, and the second 5672 is the port inside the container. This maps RabbitMQ's standard AMQP port, allowing your applications to connect to it from outside the container. P15672-15672. This maps port 15672 from the container to your host. This port is specifically for the RabbitMQ management plugin's web interface, which we'll explore shortly. RabbitMQ 3 management. This specifies the Docker image to use. RabbitMQ, the name of the official RabbitMQ image. Management, this is the tag. 3 refers to a specific major version of RabbitMQ. The management suffix is crucial as it automatically includes and enables the management plugin, providing the convenient web UI. If you omit management, you'd get a leaner image but without the UI. When you run this command for the first time, Docker will download the RabbitMQ 3 management image if it's not already on your system. This might take a few moments depending on your internet connection. Once downloaded, the container will start, and you'll see a stream of logs in your terminal indicating that RabbitMQ is starting up and its plugins are being loaded. Step 3. Verify installation via browser and terminal. Once you see messages in your terminal indicating RabbitMQ has started, look for lines like Server Startup Complete. You can verify its running status. Via web browser. Open your web browser and navigate to http localhost:15672. You should be greeted by the RabbitMQ management login page. The default username is guest. The default password is guest. Important security note: the guest user is only allowed to connect from localhost by default. This is a security measure. For any production or even shared development environment, you should always create new users with strong passwords and appropriate permissions, and then delete or restrict the guest user. For local development, it's typically fine. Via terminal Docker commands, you can open a new terminal window, leaving the current one running RabbitMQ logs, and type docker ps. This command lists all currently running Docker containers. You should see an entry for your RabbitMQ container. To stop the RabbitMQ container, go back to the terminal where it's running and press Ctrl+C or CMD+C on macOS. Since we use the RM flag, the container will be removed automatically. You can also stop a running container from a different terminal using docker stop RabbitMQ. 3.3.2 Other installation methods. Briefly mention. While Docker is excellent for local development, you might encounter other installation methods, especially in server environments. Package managers. On Linux distributions, you can often install RabbitMQ using package managers like apt debian/ubuntu or yum cent osrhel. For example, sudo apt install RabbitMQ server. Homebrew macOS. Brew install RabbitMQ. Manual installation, downloading the binaries and installing it directly. Cloud providers. Many cloud providers offer managed RabbitMQ services, e.g., Amazon MQ, CloudAMQP, abstracting away the installation and maintenance. For the purpose of this book, and for consistent learning, we will primarily rely on the Docker-based setup. 3.4 Exploring the RabbitMQ Management Plugin. The RabbitMQ Management Plugin is an invaluable tool for developers and operators alike. It provides a graphical interface to interact with your broker, inspect its state, create delete queues, monitor message flow, and much more. 3.4.1 Accessing the UI. As mentioned, once your Docker container is running, open your browser and navigate to http localhost:15672. Log in with username guest and password guest. 3.4.2 Navigating the dashboard. Upon successful login, you'll see the Overview dashboard. This provides a high-level summary of your RabbitMQ instance, including active connections, channels, and message rates. Let's briefly explore some key tabs. Overview. summarizes total connections, channels, exchanges, queues, and message rates. Connections shows active client connections, their details, and from which IP addresses they originate. Channels displays active channels, logical connections over an AMQP connection. Often, a client library opens a single connection and then multiplexes multiple channels over it. Exchanges lists all exchanges currently defined in the selected virtual host. Here, you can create new exchanges, inspect their type, direct, fan-out topic, and view their bindings. Queues lists all queues. You can inspect queue properties, durable, auto-delete, exclusive, see the number of messages ready for consumption, messages in memory, and consumer count. You can also publish messages directly to a queue, which implicitly uses the default exchange, or purge messages from a queue here. Admin allows you to manage users, virtual hosts, and permissions. This is where you would create separate users and vhosts for your applications, as discussed in Chapter 2. 3.5 Your first messages. The Hello World of RabbitMQ. Now, let's use the management UI to send and receive our first messages. This will give you a concrete feel for the message flow. Scenario. A simple Hello World work queue. We'll create a queue, publish a message into it, and then simulate a consumer pulling that message. Step 1. Declare a queue. Go to the Queues tab in the Management UI. http localhost 15672/queues. Under Add a new queue, enter HelloQueue as the name. For now, leave durable as true, it's the default and good practice, and auto-delete and exclusive as false. Click Add Queue. You should now see HelloQueue listed in your queues table. Step 2. Publish a message. Since we haven't written any code yet, we can use the Management UI to publish. Click on the HelloQueue row in the Queues table. This takes you to its detail page. Scroll down to the Publish Message section. In the Payload text area, type Hello, RabbitMQ World. You can leave the Headers and Properties sections as default for now. Click the Publish Message button. Go back to the main Queues tab. You should now see that HelloQueue has ready one message. This means one message is waiting in the queue. Step 3. Simulate a consumer and get the message. Go back to the HelloQueue detail page, click on HelloQueue in the list. Scroll down to the Get Messages section. You can leave messages set to 1, the default, and acknowledge mode as automatic ACK. This means RabbitMQ assumes the message is processed successfully as soon as it's delivered. In real applications, you'd use manual ACK for reliability. Click the Get Messages button. RabbitMQ will retrieve the message. You'll see a panel appear below with the message details, including its payload. Hello, RabbitMQ World. Look at the Ready count for HelloQueue on the main Queues tab. It should now be 0. The message has been consumed and removed from the queue. This simple exercise demonstrates the full path of a message: producer management UI, message, payload and properties, queue, HelloQueue, consumer management UI, get function. It implicitly used the default exchange, also known as the anonymous or empty string exchange, which is a predefined direct exchange that routes messages to queues with a routing key identical to the queue name. 3.6 Common initial hurdles and troubleshooting. Even with Docker, you might encounter minor hiccups. Here are some common issues and their solutions. Localhost 15672 refused to connect, or this site can't be reached. Docker not running, ensure Docker desktop is running on your machine. Container not running, check Docker PS. If the RabbitMQ container isn't listed, revisit the Docker run command and check for errors in the terminal where you ran it. Port conflict. Another application might be using port 15672 or 5672. You can change the host port mapping in the Docker run command, e.g. P15673, 15672, to use 15673 on your host. Firewall. Your operating system's firewall might be blocking access. Ensure ports 5672 and 15672 are open for incoming connections. Guest login fails. Some older Docker images or custom configurations might have different default credentials. Double-check the image's documentation if this happens. However, for RabbitMQ 3 management, guest is standard. Ensure you are connecting from localhost 127.0.0.1. As mentioned, the guest user is restricted to local connections for security. Connection refused in your code later on. This typically means your application can't reach RabbitMQ. Verify the IP address and port in your code should be localhost or 127.0.0.1 and 5672. Confirm the RabbitMQ container is still running, Docker PS. 3.7 Beyond Hello World. What's next? You've successfully installed RabbitMQ, navigated its management interface, and sent your first message. This is a crucial start. While the management UI is great for inspection and simple testing, real-world applications interact with RabbitMQ using client libraries in various programming languages. In the next chapter, we will leave the management UI for a bit and dive into using actual code to implement the fundamental messaging patterns, starting with the simplest. The work queue, which you just briefly experienced, will show you how to write producers and consumers that connect to RabbitMQ programmatically, giving you the power to integrate robust asynchronous communication into your own applications. Chapter 4. Basic Messaging Patterns. Work Queues and Fanout. In the previous chapter, you successfully installed RabbitMQ and sent your first message using the management UI. While useful for quick tests, real applications interact with RabbitMQ programmatically using client libraries. This chapter focuses on two fundamental messaging patterns: the work queue, also known as a task queue, and the fanout pattern, also known as publish-subscribe or pub-sub. These patterns illustrate how messages can be distributed to either a single worker or broadcast to multiple consumers. For clarity and practical demonstration, we will use Python for all code examples in this book. Python has a clear syntax, and its Pika library for AMQP is widely used, making the concepts easily transferable to other languages and their respective RabbitMQ client libraries. 4.1 Client Libraries in Action. Setting up. Regardless of your chosen language, the core steps to interact with RabbitMQ are similar. Establish a connection. Connect to the RabbitMQ broker. Create a channel. Channels are the primary way to interact with the AMQP protocol over a connection. Multiplexing channels over a single connection is more efficient than opening a new connection for every operation. Declare queues exchanges. Inform RabbitMQ about the queues and exchanges you intend to use. Publish consume messages. Send messages to exchanges or receive messages from queues. To get started, if you're following along with Python, ensure you have the Pika library installed. Open your terminal and run pip install Pika upgrade. 4.2 The work queue pattern. Distributing tasks. The work queue pattern is designed for distributing time-consuming tasks among multiple workers, consumers. Imagine you have a backend process that needs to resize images, generate PDFs, or send out bulk emails. These tasks can take a while, and you don't want your main application thread to be blocked waiting for them to complete. A work queue allows you to offload these tasks to dedicated workers, significantly improving the responsiveness and scalability of your application. How it works: a producer sends task messages to a queue. Multiple consumers, workers, listen on that same queue. Each message from the queue is delivered to only one of the active consumers. If there are multiple consumers, RabbitMQ will distribute the messages among them in a round-robin fashion by default. This ensures that each task is processed once and that the workload is shared. 4.2.1 Implementing the work queue. Let's create two Python scripts, one for the producer, which will be a newDeskPy, and one for the consumer, which we'll call workerPy. A. The producer newDeskPy. This script will take a message from the command line arguments and send it to our work queue. Import Pika. Import sys. 1. Establish a connection. Default connection params for localhost :5672. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. 2. Declare the queue. Task queue will be our queue name. Durable equals true means the queue will survive a RabbitMQ server restart. Channel queue declare, queue equals task queue, durable equals true. 3. Prepare the message. Get message from command line arguments, default to hello world. Message equals joints is argv1 or hello world. 4. Publish the message. Default exchange is a direct exchange that routes to queues matching the routing key. Routing key equals task queue means send it to the queue named task queue. Properties equals Pika basic properties. Deliver mode equals 2 makes the message persistent. Channel basic publish. Exchange equals routing key equals task queue. Body equals message. Properties equals Pika basic properties. Deliver mode equals Pika spec persistent deliver mode hash. Make message persistent. Print fx sent message. Close the connection. Connection close. Key parts of producer script. Pika blocking connection. This creates a synchronous connection. While Pika supports asynchronous connections, blocking connection is simpler for initial examples. Channel equals connection channel. All operations are done on a channel. You can create multiple channels over one connection. Channel queue declare. Queue equals task queue, durable equals true. This declares the queue. If it doesn't exist, RabbitMQ will create it. If it exists with the same properties, nothing happens. Durable equals true is crucial here. It means the queue itself will survive if the RabbitMQ server restarts. Exchange equals. This specifies the default exchange. When you publish to the default exchange, a message is routed to the queue whose name exactly matches the routing key. Routing key equals task queue. The message is directed to task queue. Deliver mode equals Pika spec, persistentdlivry or simply deliver mode. This makes the message persistent. This means if the RabbitMQ server shuts down, the message will not be lost, assuming the queue is also durable. Be the consumer worker pie. This script will receive messages from task queue and simulate work by pausing for a few seconds based on the message content. Import Pika. Import time. 1. Establish a connection. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. 2. Declare the queue again to ensure it exists if consumer starts first. Channel queue declare. Queue equals task queue. Durable equals true. Important. Set quality of service (CoS) for fair dispatch. Per fetch count equals 1 tells RabbitMQ not to send more than one message to a consumer at a time until it acknowledges the previous one. Channel basic goes per fetch count equals 1. 3. Define the callback function. Def callback ch method properties body print fx received body.decode time sleep body.count b hash simulate work e.g. hello takes 3s. Print x done. Hash 4. Acknowledge the message. Hash tell RabbitMQ the message was successfully processed and can be removed from the queue. Ch basic hack deliveritEgg equals method.deliveritEgg. 5. Start consuming. Basic consume takes a callback function to handle messages. AutoAck equals false means the consumer will explicitly acknowledge messages. Channel basic consume queue equals task queue. On message callback equals callback, AutoAck equals false. Print waiting for messages. To exit press Ctrl+C. Channel start consuming. Key parts of consumer script. Channel queue declare, queue equals task queue, durable equals true. The consumer also declares the queue. This is a good practice to ensure the queue exists even if the consumer starts before the producer. Channel basic goes, per fetch count equals 1. This sets the quality of service for this consumer. Per fetch count equals 1 means RabbitMQ will only send one message to this consumer at a time. It will wait for the consumer to acknowledge the message, basic hack, before sending another. This prevents one fast worker from hogging all messages while a slow worker starves, enabling fair dispatch. Without this, messages would be delivered round-robin even if a worker isn't finished with the previous message, leading to uneven workloads and potential message timeouts. Callback ch method properties body. This function is executed Pika every time a message is received. Ch, the channel object. Method contains delivery metadata like deliveritEgg. Properties. Message properties like deliverimode. Body, the message payload your hello world, text. Ch basic hack deliveritEgg equals method.deliveritEgg. This command sends an acknowledgement to RabbitMQ, telling it that the message has been successfully processed and can be safely deleted from the queue. If a consumer crashes before acknowledging, RabbitMQ will redeliver the message to another available consumer. Channel basic consume registers the callback function to be called for messages from task queue. AutoAC equals false explicitly tells RabbitMQ that we will manually acknowledge messages after processing. Channel start consuming. This enters a blocking loop that waits for data, runs callbacks, and generally handles networking. 4.2.2 Running the work queue example. Start your RabbitMQ Docker container if it's not already running. Docker run it rm name RabbitMQ, P5672 5672, P15672 15672 RabbitMQ, 3 management. Open 2 or more separate terminal windows for consumers. In each of these new terminals, start a WorkerPy consumer, Python WorkerPy. You'll see waiting for messages. To exit, press Ctrl+C in each. Open another terminal window for the producer. Send messages using newtaskpy. Python newtaskpy first message. Python newtaskpy second message. Python newtaskpy third message. Python newtaskpy fourth message. Notice how messages with more dots simulate longer tasks. Observe your WorkerPy terminals. You'll see them receiving messages and processing them. Because of durable equals true, persistentdlivr_ymode, and prefetchCount equals 1, messages are distributed fairly, and no messages are lost if a worker goes down. If you kill one WorkerPy while it's processing, RabbitMQ will eventually redeliver that message to another available worker. This demonstrates how a work queue efficiently distributes tasks among available workers, enhancing system responsiveness and scalability. 4.3 The fanout pattern. Broadcasting messages. The fanout pattern is used when you want to broadcast a message to multiple consumers simultaneously. Unlike the work queue, where each message is processed by only one consumer, in the fanout pattern, every consumer connected to the relevant exchange receives a copy of the message. This is often called publish-subscribe or pub/sub. How it works: a producer sends messages to a fanout exchange. Consumers create their own queues and bind them to this fanout exchange. When a message arrives at the fanout exchange, it is duplicated and sent to all queues bound to that exchange. Each consumer then receives and processes its own copy of the message from its dedicated queue. This allows multiple, independent applications to react to the same event. 4.3.1 Implementing the fanout pattern. For this, we'll have a producer emit logpy that sends log messages, and consumers receive a logpy that receive all logs. Each receive a logpy instance will get a copy of every log message. The producer emit logpy. This script will send a log message to a fanout exchange. Import Pika. Import says connection equals Pika blocking connection, Pika.connection parameters, host equals localhost. Channel equals connection channel. 1. Declare the fanout exchange. Logs will be our exchange name. Fanout is the type. Durable equals true for the exchange is also a good practice. Channel exchange declare exchange equals logs, exchange type equals fanout, durable equals true. 2. Prepare the message. Message equals joints is argv1 or info hello world. 3. Publish the message to the exchange. For fanout, routing key is ignored, so we use an empty string. Channel basic publish. Exchange equals logs, routing key equals, body equals message. Printf sent, message. Connection close. Key parts of producer script. Channel exchange declare, exchange equals logs, exchange type equals fanout, durable equals true. This declares the logs exchange as a fanout type. Exchange equals logs, routing key equals, messages are now published to the logs exchange. The routing key is ignored by fanout exchanges, so we pass an empty string. B. The consumer receive a logpy. This script will create a queue, bind it to the logs fanout exchange, and then receive all log messages broadcast by the producer. Import Pika. Import says connection equals Pika blocking connection, Pika.connection parameters, host equals localhost, channel equals connection channel. 1. Declare the exchange. Consumer also declares to ensure it exists. Channel exchange declare, exchange equals logs, exchange type equals fanout, durable equals true. 2. Declare an exclusive, non-durable auto-delete queue for this consumer. As queue name tells RabbitMQ to generate a unique, non-shared name. Exclusive equals true means this queue will be deleted when the connection closes. Result equals channel queue declare, queue equals. Exclusive equals true, durable equals false, auto-delete equals true. Queue name equals result method queue. 3. Bind the queue to the exchange. No routing key needed for fanout binding. Channel queue bind exchange equals logs, queue equals queue name. Print waiting for logs. To exit press CTRL plus C. 4. Define the callback function. Def callback, ch method properties body, print fx body.decode. 5. Start consuming. AutoAC equals true because these logs are less critical. We don't need persistence if consumer dies. Channel basic consume, queue equals queue name, on message callback equals callback, AutoAC equals true. Channel start consuming. Key parts of consumer script. Channel exchange declare, exchange equals logs, exchange type equals fanout, durable equals true. The consumer also declares the exchange, ensuring it exists. Result equals channel queue declare, queue equals, exclusive equals true, durable equals false, auto-delete equals true. Queue equals, provides an empty string for the queue name. RabbitMQ will generate a unique, random queue name for us e.g. AMCGen JZMLZ XNYGA 3P0 QLZ F2S DWW. This is perfect for transient consumers, each wanting their own log copy. Exclusive equals true makes this queue exclusive to this connection. Other connections cannot use this queue. Durable equals false. The queue will not survive a broker restart. Auto-delete equals true. The queue will be deleted automatically when the last consumer disconnects. This cleans up temporary queues. Queue name equals result method queue. Retrieves the unique queue name generated by RabbitMQ. Channel queue bind, exchange equals logs, queue equals queue name. This is the crucial step. It tells the logs exchange to send a copy of every message it receives to this newly created unique queue. AutoAC equals true. For simplicity in this fanout example, we're using automatic acknowledgements. This means RabbitMQ removes the message from the queue as soon as it's delivered to the consumer. For critical messages, AutoAC equals false and manual basic hack are preferred. 4.3.2 Running the fanout example. Start your RabbitMQ Docker container if it's not already running, or restart it to clear previous state if desired. Open 2 or more separate terminal windows for consumers. In each of these terminals, start a receivealogpy consumer, Python receivealogpy. Notice that each consumer will declare its own unique, temporary queue. You can verify this in the RabbitMQ Management UI on the Queues tab. They will have names like AMCGen. Open another terminal window for the producer. Send messages using emitLogPy, Python emitLogPy. This is an important log message. Python emitLogPy, another log for the system. Python emitLogPy warning, disk space low. Observe your receivealogpy terminals. Each one should receive every message sent by emitLogPy. If you stop one receivealogpy and restart it, it will create a new asterisk unique queue and only receive messages sent from that point forward. This demonstrates the fanout pattern's ability to broadcast messages to all interested parties. Perfect for event-driven architectures, logging, or notifications where multiple services need to react to the same event. 4.4 Summary and what's next? You've now successfully implemented 2 foundational messaging patterns using RabbitMQ and Python. Work queues. Efficiently distribute tasks among a group of workers, ensuring each task is processed once and providing fair dispatch. Fanout. Broadcast messages to all connected consumers, enabling publish-subscribe functionality for event distribution. You've also gained practical experience with declaring queues and exchanges, publishing messages, consuming messages using callbacks, and using basic message properties like deliver remote for persistence. More importantly, you've seen the power of durable queues and basicos for robust work queues, and exclusive and auto-delete queues for dynamic pub/sub. These 2 patterns only scratch the surface of RabbitMQ's routing capabilities. In the next chapter, we'll explore more sophisticated routing schemes using direct and topic exchanges, allowing you to filter and route messages with much greater precision. Chapter 5. Smart Routing with Direct and Topic Exchanges. In the previous chapter, we introduced the basic work queue and fanout patterns. while fan-out broadcasts messages to all listeners, and work queues efficiently distribute tasks evenly, sometimes you need more granular control over message delivery. What if you want different consumers to receive specific types of messages or filter messages based on dynamic criteria? This is precisely where direct exchanges and topic exchanges shine. They allow for smart routing by leveraging the message's routing key. Recall from Chapter 2, producers send messages to an exchange with a routing key. The exchange then uses its type and the message's routing key to decide which queues to send the message to via bindings, which may also have binding keys. This chapter will delve into direct and topic exchanges, showing how to leverage these concepts for flexible and powerful message routing. 5.1 Direct Exchange. Targeted routing. The direct exchange routes messages to queues whose binding key exactly matches the message's routing key. It's the simplest form of routing based on a key match. Imagine it as a precise postal service where a letter with a specific address goes only to that address. How it works. A producer sends a message to a direct exchange with a specified routing key, e.g., error, warning, info. Queues are bound to this direct exchange with one or more binding keys. If a message's routing key exactly matches a queue's binding key, the message is delivered to that queue. If multiple queues are bound with the same binding key, the message will be delivered to all of them, similar to a fan-out, but only for messages matching that specific key. However, this is less common for direct exchanges, which are typically used for distinct, well-defined categories. 5.1.1 Implementing Direct Exchange. Let's use a logging example. We want to send log messages with different severities, info, warning, error. Different consumers might only be interested in certain severities, e.g., one consumer only cares about error messages, another cares about all warning and error messages. The producer, emit log direct pi. This script will take a log severity routing key and a message as arguments. Import pica. Import sys. Connection equals pica blocking connection, pica.connection parameters, host equals localhost, channel equals connection channel. 1. Declare a direct exchange. Direct logs will be our exchange name, direct type. Channel exchange declare exchange equals direct logs, exchange type equals direct, durable equals true. 2. Get severity and message from command line arguments. Severity equals sysargv1 if len, sysargv1 else info. Message equals join sysargv2 or hello info. 3. Publish the message to the exchange with the specified severity as routing key. Channel basic publish. Exchange equals direct logs. Routing key equals severity. Hash this is the routing key. Body equals message. Print fx sent, severity message. Connection close. Be the consumer, receive a log direct pi. This script will receive and process specific log severities based on command line arguments, e.g., Python receive a log direct pi warning error. Import pica. Import sys. Connection equals pica blocking connection, pica.connection parameters, host equals localhost, channel equals connection channel. 1. Declare the direct exchange, ensure it exists. Channel exchange declare, exchange equals direct logs, exchange type equals direct, durable equals true. 2. Declare an exclusive, non-durable auto-delete queue for this consumer. This ensures each consumer gets its own unique queue. Result equals channel queue declare, queue equals, exclusive equals true. Quename equals result method queue. 3. Get desired severities, binding keys, from command line arguments. Severities equals sysargv1. If not severities, sysstd usage, %s info warning error \n %sysargv0. Sysexit 1. 4. Bind the queue to the exchange for each specified severity. For severity and severities, channel queue bind. Exchange equals direct logs. Queue equals quename. Routing key equals severity hash this is the binding key. Print waiting for direct logs. To exit press ctrl plus C. 5. Define the callback function. Def callback ch method properties body. Print fx method routing key body.decode. 6. Start consuming. AutoAC equals true for simplicity here. Channel basic consume. Queue equals quename. OnMessage callback equals callback. AutoAC equals true. Channel start consuming. 5.1.2 Running the direct exchange example. Start your RabbitMQ Docker container. Open several terminal windows. In one terminal, start a consumer interested in error logs, Python receivealog directpy error. In another terminal, start a consumer interested in both warning and error logs, Python receivealog directpy warning error. In a third terminal, start a consumer interested in info logs, Python receivealog directpy info. In a fourth terminal, send messages using emitlig directpy, Python emitlig directpy info user logged in will go to info consumer. Python emitlig directpy warning disk space low will go to warning error consumer. Python emitlig directpy error database connection failed will go to both error and warning error consumers. Python emitlig directpy debug message will not go to any consumer if no one is bound to debug. Observe how messages are routed precisely to the consumers that have bound their queues with a matching severity routing key. This demonstrates direct exchange's power for targeted distribution of messages based on exact key matches. 5.2 Topic Exchange, Pattern-Based Routing. The topic exchange is the most flexible and commonly used exchange type for complex routing scenarios. It's like an advanced direct exchange that allows for pattern matching in the routing keys. Imagine a newspaper subscription where you can subscribe to topics like sports, football, or just news. To get all news, or Europe, hash to get all news from Europe regardless of specific country or city. How it works. A producer sends a message to a topic exchange with a routing key that is typically a list of words, delimited by dots, e.g., stock.ust.nyse by. Queues are bound to the topic exchange with binding keys that are also dot-delimited words, but can include two special wildcards. Asterisk matches exactly one word anywhere in the binding key. Hash matches 0 or more words anywhere in the binding key. The message's routing key is matched against the queue's binding key. If they match the pattern, the message is delivered. 5.2.1 Implementing Topic Exchange. We'll extend our logging example to include origin and severity. For instance, log messages could be like system.auth.info, web.error.debug, mobile notification warning. The producer, emitlig topic pi. This script will take a routing key, topic, and a message as arguments. Import pika. Import sys. Connection equals pika blocking connection, pika.connection parameters, host equals localhost, channel equals connection channel. 1. Declare a topic exchange. Topic logs will be our exchange name, topic type. Channel exchange declare exchange equals topic logs, exchange type equals topic, durable equals true. 2. Get routing key, topic, and message from command line arguments. Routing key equals sysargv1 if len, sysargv1 else anonymous.inf. Message equals join sysargv2 or hello world. 3. Publish the message with the specified routing key. Channel basic publish. Exchange equals topic logs. Routing key equals routing key. Hash the topic for routing. Body equals message. Printf sent, routing key message. Connection close. B. The consumer, receivealog topic pi. This script will subscribe to specific topics or patterns based on command line arguments, e.g. Python receivealog topic pi error, cron, warning. Import pika. Import sys. Ensure at least one binding key is provided. If len sysargv2, sysstderite, usage, %s binding key, n %sysargv0. Sysexit 1. Connection equals pika blocking connection, pika.connection parameters, host equals localhost, channel equals connection channel. 1. Declare the topic exchange, ensure it exists. Channel exchange declare, exchange equals topic logs, exchange type equals topic, durable equals true. 2. Declare an exclusive, non-durable auto-delete queue for this consumer. Result equals channel queue declare, queue equals, exclusive equals true, queuename equals result method queue. 3. Get desired binding keys, topics to subscribe to, from command line arguments. Binding keys equals sysargv1. 4. Bind the queue to the exchange for each specified binding key. For binding key and binding keys. Channel queue bind. Exchange equals topic logs. Queue equals queuename. Routing key equals binding key hash. This is the binding key for pattern matching. Print waiting for topic logs. To exit press CTRL+C. 5. Define the callback function. Def callback, ch method properties body, print fx method routing key body dot decode. 6. Start consuming, autoac equals true for simplicity. Channel basic consume. Q equals QName. On message callback equals callback. Autoac equals true. Channel start consuming. 5.2.2, running the topic exchange example. Start your RabbitMQ Docker container. Open several terminal windows. In one terminal, start a consumer interested in all error messages, regardless of their origin. Python receivalig topic py error. In another terminal, start a consumer interested in warning or info messages from web or mobile sources. Python receivalig topic py web warning mobile.info. In a third terminal, start a consumer interested in all messages, hash matches everything. Python receivalig topic py. In a fourth terminal, send messages using emitlig topic py. Python emitlig topic py system.auth.info. User Alice logged in. Python emitlig topic py web API error. API endpoint users 500 error. We'll go to error consumer and hash consumer. Python emitlig topic py cron job warning. Daily report generation took too long. Python emitlig topic py mobile.app.info. User Bob updated profile. Python emitlig topic py web.checkout.debug, checkout process step 3. Only hash consumer will get this. Observe how the topic exchange routes messages based on the pattern matching rules. This powerful flexibility allows you to build highly segmented and dynamic message distribution systems. 5.3. Choosing the right exchange type. Summary of when to use each exchange type. Direct exchange, use when you need to route messages to a specific queue or a small, predefined set of queues based on an exact match of the routing key. Analogy, direct mail specifying the exact recipient and address. Example, distributing tasks to specific worker types, process image versus process video. Fan-out exchange, use when you need to broadcast messages to all interested consumers that connect to that exchange. Routing keys are ignored. Analogy, a public announcement or loudspeaker. Example, real-time updates, stock ticks, logging all log messages to all log processing services, notification system where all clients need to know about an event. Topic exchange. Use when you need flexible, pattern-based routing where consumers can subscribe to various topics or subtopics using wildcards. This is the most versatile for complex routing hierarchies. Analogy. Subscribing to specific categories or subcategories of a blog or news service. Example, routing events in a microservices architecture, e.g., order created, order shipped, product updated, complex logging systems based on source and severity. 5.4 Summary and what's next. You've now mastered the ability to route messages intelligently and selectively using RabbitMQ's direct and topic exchanges. This is a significant step towards building sophisticated message-driven applications that can distribute information precisely where it needs to go. However, sending messages is only one part of the equation. What happens if a message fails to be processed, or if the RabbitMQ server itself goes down? In the next chapter, we'll delve into the crucial topic of reliability. We'll cover message acknowledgements, persistence, and durability, ensuring that your messages are not just routed correctly, but also delivered and processed safely, even in the face of failures. Chapter 6. Ensuring reliability. Messages, acknowledgements, and durability. Up to this point, we've focused on getting messages from producers to consumers using various routing patterns. But what happens if a network connection drops while a message is in transit? Or if a consumer crashes in the middle of processing a message? What if the RabbitMQ server itself restarts? In such scenarios, simply sending messages isn't enough. We need guarantees that messages are not lost and are processed reliably, exactly once, or at least once. This chapter delves into the core mechanisms RabbitMQ provides for reliability: message acknowledgements, durability, and persistence. These features are crucial for building robust message-driven systems where data integrity and task completion are paramount. 6.1 Message acknowledgements. Confirming delivery and processing. When RabbitMQ delivers a message to a consumer, it doesn't immediately remove it from the queue. Instead, it waits for an acknowledgement, ACK, from the consumer. An acknowledgement is a signal from the consumer to RabbitMQ that the message has been successfully received and fully processed. Why are acknowledgements so important? Guaranteed processing. If a consumer receives a message, but crashes before sending an ACK, RabbitMQ will redeliver that message to another available consumer, or back to the same consumer if it restarts. This ensures the message is eventually processed, preventing message loss. Without ACKs, if a consumer receives a message and then fails, that message would be considered processed and removed from the queue, leading to data loss. Flow control. Acknowledgements are tied to the prefetch-count quality of service, (QoS), we saw in Chapter 4. RabbitMQ won't send more messages to a consumer than its prefetch-count limit until it acknowledges pending messages. This mechanism prevents a fast producer from overwhelming a slow consumer and ensures fair message distribution. 6.1.1 Automatic versus manual acknowledgements. Automatic acknowledgements, AutoAC equals true, the simplest mode. RabbitMQ considers a message processed and removes it from the queue as soon as it sends the message to the consumer. This is suitable for very simple, non-critical scenarios, like the receive-a-log fanoutpy example, where lost logs are acceptable. However, if the consumer crashes immediately after receiving the message, but before processing it, the message is lost. Manual acknowledgements, AutoAC equals false, the recommended and default approach for reliable messaging. The consumer explicitly sends an ACK back to RabbitMQ after it has successfully processed the message. 6.1.2 Negative acknowledgements, NACKs and rejections. Sometimes, a consumer might receive a message, but be unable to process it successfully, e.g., corrupted data, external service unavailable, application error. RabbitMQ provides mechanisms for negative acknowledgements. basic NAC, deliver it egg, multiple equals false, requeue equals true, a general negative acknowledgement. Multiple equals true. NAC case all unacknowledged messages up to the deliver it egg. Requeue equals true, tells RabbitMQ to put the message back into the queue for redelivery to another consumer. If false, the message is discarded or sent to a dead letter exchange if configured, which we'll cover in Chapter 7. basic reject, deliver it egg, requeue equals true, similar to basic NAC but only for a single message. Requeue equals true, puts the message back for redelivery. If false, it's discarded. Important considerations for requeuing. Indefinite redelivery of problematic messages can lead to message loops or poison pill messages constantly consuming resources. For persistent failures, consider a dead letter queue strategy, Chapter 7, rather than endless requeuing. 6.1.3 Example with manual acknowledgements. Let's revisit our worker pie from Chapter 4, which already used AutoAC equals false and basic hack. This is a prime example of manual acknowledgement in action. Producer, NewDeskPy, no changes needed. It already sets delivery mode equals persistent delivery mode. Code unchanged from Chapter 4. Import Pika. Import sys. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. Channel queue declare, queue equals task queue. Durable equals true. Message equals join sys argv1 or hello world. Channel basic publish. Exchange equals routing key equals task queue, body equals message. Properties equals Pika basic properties. Delivery mode equals Pika spec persistent delivery mode hash. Make message persistent. Printf sent, message. Connection close. Consumer worker pie, a review of the relevant parts. Relevant parts from Chapter 4. Import Pika. Import time. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. Channel queue declare, queue equals task queue. Durable equals true. Channel basicos, prefetch count equals 1, hash ensures fair dispatch. One unacknowledged message at a time. Def callback, method properties body. Print fx received body.decode. Hash simulate work and potential failure. If fail in body.decode, lower. Print x simulating failure, not acknowledging. Hash you would typically basic NAC. Requeue equals true/false or basic reject depending on the failure type. Hash for this demo, simply don't act to simulate crash. RabbitMQ will redeliver after connection lost. Hash let's add a basic knack for explicit example if it contains knack. If knack in body.decode, lower. Ch basic knack, deliver it egg equals method dot deliver it egg, req equals true. Print x knacked and requeued. Else timesleep body dot count b. Print x done. Ch basic hack, deliver it egg equals method dot deliver it egg, hash manual acknowledgement. Channel basic consume, q equals task q. On message callback equals callback, auto ack equals false. Print waiting for messages. To exit press CTRL plus C. Channel start consuming. Experiment with acknowledgement. Run a worker py and then send a message Python new desk py important task. The worker processes and acts. Send another message Python new desk py task that will fail. The worker starts processing, but then you abruptly kill the worker process, e.g., Control plus C. Because the worker didn't ACK, RabbitMQ will detect the lost connection and redeliver task that will fail to another available worker, or if you restart the original worker, it will get it again. Send a message Python new desk py task to knack. Observe the worker NACKing it and seeing it potentially redelivered. This behavior is fundamental for building reliable systems. Messages are not presumed processed until the consumer explicitly confirms it. 6.2 Durability and persistence. Surviving broker restarts. While acknowledgements protect against consumer failures, what happens if the RabbitMQ broker itself crashes or restarts? By default, queues and messages are transient in memory and would be lost. This is where durability and persistence come in. 6.2.1 Durable queues. A durable queue is a queue that will survive a RabbitMQ server restart. If you declare a queue as durable, it will be recreated in the same state, with the same name and properties, after a server restart. If you try to declare a durable queue with the same name as an existing non-durable queue, or vice versa, RabbitMQ will throw an error. How to declare durable queues. In QEDeclare, set durable equals true. Example, channel QEDeclare, q equals myDurableQ, durable equals true. 6.2.2 Persistent messages. Even if a queue is durable, messages within it might not be. Messages also need to be marked as persistent to survive a broker restart. If you have a durable queue but send non-persistent messages to it, those messages will be lost if the broker restarts. How to declare persistent messages. When publishing, set the deliverMode property of the basic properties to 2 or picaspec PARSISTNTDLIVRYMODE. Example, properties equals pica basic properties, deliverMode equals picaspec persistent deliverMode. Important relationship. For messages to truly survive a broker restart, both the queue must be durable and the messages must be persistent. If one is missing, you risk message loss. 6.2.3 Example with persistence. Our new task py and worker py from Chapter 4 already incorporate durability and persistence. Let's recap them and demonstrate their effect. Recap of new task py, producer. Channel QEDeclare, q equals task q, durable equals true, hash durable q. Channel basic publish. Exchange equals. Routing key equals task q. Body equals message. Properties equals pica basic properties. DeliverMode equals picaspec persistent deliverMode, hash persistent message. Recap of worker py, consumer. Channel QEDeclare, q equals task q, durable equals true, hash durable q. Demonstrating durability persistence. Ensure no worker py consumers are running. Send several messages using newDeskPy. Python newDeskPy, this is a durable message. Python newDeskPy, another one for the queue. Check the RabbitMQ management UI, http localhost 15672. On the Queues tab, click Task Queue. You should see Ready 2 messages. Under Features, it should indicate Durable, yes. Stop the RabbitMQ Docker container. Go to the terminal where RabbitMQ is running and press Ctrl plus C. Or open a new terminal and run docker stop RabbitMQ. Restart the RabbitMQ Docker container. Docker run it rm name RabbitMQ, P5672 P15672 15672 RabbitMQ, 3 management. Wait for it to start up. Check the RabbitMQ management UI again. Navigate to your task queue. You should see Ready 2 or whatever number of messages you sent before stopping. The messages have survived the broker restart. Now, start WorkerPy Consumer Python WorkerPy. It will pick up and process the messages that survived the restart. This experiment vividly demonstrates the power of durable queues and persistent messages in protecting your data against broker failures. 6.3 When not to use high reliability and its cost. While reliability is often critical, it's essential to understand its trade-offs. Performance overhead. Writing messages to disk, for persistence, is slower than keeping them in memory. Requesting acknowledgements adds network round trips. Complexity. Managing acknowledgements, especially NAC case and rejections, handling redeliveries, and potential poison pills adds complexity to your consumer logic. Consider skipping durability and persistence for ephemeral data, real-time metrics, volatile logs where some loss is acceptable. High throughput, low latency scenarios, where raw speed is more important than absolute guarantee of delivery. Reconstructible data. If data can be easily regenerated by the producer, persistence might be overkill. Even in these cases, acknowledgements, without persistence, might still be useful to ensure timely processing and detect consumer failures, as messages might live in memory long enough for redelivery. 6.4 Summary and what's next. You've now armed yourself with the fundamental tools for building reliable message-driven systems using RabbitMQ. Message acknowledgements. Ensuring messages are processed at least once or exactly once with proper consumer design by confirming successful processing. Basicos and prefetch count for fair dispatch and preventing consumer overload. Durable queues. Protecting the queue definitions themselves across broker restarts. Persistent messages. Protecting the messages within durable queues across broker restarts. These mechanisms are foundational for handling real-world scenarios where applications or the broker itself might fail. However, what happens when messages consistently fail to process? Or when messages expire? The next chapter, Advanced Message Features, will introduce you to more sophisticated tools like dead letter exchanges and time to live, allowing you to gracefully handle unprocessable messages and manage message lifecycles. Chapter 7, Advanced Message Features, Dead Letters, TTL, and Policies. In the previous chapter, we established a strong foundation for reliability using acknowledgements and durability. However, distributed systems are inherently complex, and sometimes messages encounter situations that prevent them from being processed successfully, or they simply become irrelevant after a certain period. RabbitMQ provides powerful advanced features to handle these scenarios gracefully, preventing message loss, allowing for error investigation, and enabling efficient message lifecycle management. This chapter will delve into 3 key advanced message features: dead letter exchanges, DLX, time to live, TTL, and policies, which offer fine-grained control over message behavior and lifecycle. 7.1 Dead letter exchanges, DLX. Handling undeliverable messages. A dead letter exchange, DLX, is a regular exchange, which can be of any type, direct, fan-out, or topic, that acts as a graveyard for messages that could not be delivered or processed successfully. When a message becomes dead-lettered, it is automatically republished to the DLX. From there, it can be routed to a dedicated dead letter queue where consumers can inspect it, attempt reprocessing, or simply log it for later analysis. Messages are dead-lettered for 3 main reasons. NAC'd with requeue equals false or rejected. A consumer explicitly sends a negative acknowledgement, basic NAC or basic reject, with the requeue parameter set to false. This signals that the message is problematic and should not be put back into the original queue. Message TTL expired. The message remains in the queue for longer than its configured time to live, TTL value, which we'll discuss next. Queue length limit exceeded. The queue grows beyond its maximum length via xMaxLength argument, and the message is consequently dropped from the head of the queue. By configuring a DLX, you gain visibility into failed messages, enabling you to build error handling mechanisms rather than silently dropping problematic data. 7.1.1 Configuring a DLX. To use a DLX, you need to declare a dead letter exchange, and optionally a dead letter queue bound to it. Configure the source queue to specify which exchange should be used as its dead letter exchange. Let's illustrate with an example where messages that fail to process are sent to a dead letter queue. A. Producer looks by. This will be a simple producer, sending messages with a routing key, task. Import Pika. Connection equals Pika blocking connection, Pika.connection parameters, host equals localhost, channel equals connection channel. Declare a normal exchange for our messages. Channel exchange declare, exchange equals main exchange, exchange type equals direct, durable equals true. Publish a few messages. For I in range 5. Message equals F task, I+1. Channel basic publish. Exchange equals main exchange. Routing key equals task. Body equals message. Print FX sent, message. Connection close. B. Consumer with looks by. This consumer will intentionally knack some messages with requeue equals false, sending them to the DLX. Import Pika. Import time. Import sys. Connection equals Pika blocking connection, Pika.connection parameters, host equals localhost, channel equals connection channel. 1. Declare the dead letter exchange and queue. This is where dead lettered messages will go. DL's exchange name equals deadalter exchange. DLX queue name equals deadalter queue. Channel exchange declare, exchange equals DL's exchange name. Exchange type equals fanout, durable equals true. Channel queue declare, queue equals DLX queue name, durable equals true. Channel queue bind, exchange equals DL's exchange name. Queue equals DLX queue name. Printf declare DLX queue. DLX queue name. 2. Configure the main queue with dead letter arguments. Main queue name equals main queue. Channel queue declare. Queue equals main queue name. Durable equals true. Arguments equals x dead letter exchange. DL's exchange name. Bind main queue to main exchange. Channel queue bind, exchange equals main exchange. Queue equals main queue name, routing key equals task. Printf main queue name, configured with DLX. Channel basic goes, prefetch count equals 1. Def callback, ch method properties body. Message content equals body.decode. Printfx received, message content. Hash simulate failure for messages containing 3 or 5. If 3 in message content or 5 in message content. Printf processing failed for message content, NACKing and sending to DLX. Ch basic knack, deliveritEgg equals method.deliveritEgg, requeue equals false, hash important. Requeue equals false. LC, time sleep, 1 hash simulate work. Printfx processed, message content, acknowledging. Ch basic hack, deliveritEgg equals method.deliveritEgg. Channel basic consume, queue equals main queue name, on message callback equals callback, autohack equals false. Print, waiting for messages for main queue. To exit press Ctrl+C. Channel start consuming. DLX consumer pi. This consumer will simply listen to the dead letter queue. Import Pika. Connection equals Pika blocking connection, Pika.connection parameters, host equals localhost. Channel equals connection channel. DLX queue name equals deadalter queue. Channel queue declare, queue equals DLX queue name, durable equals true. Def callback, ch method properties body. Printf DLX received dead lettered message, body.decode. Ch basic hack, deliveritEgg equals method.deliveritEgg. Channel basic consume, queue equals DLX queue name, on message callback equals callback, autohack equals false. Print, waiting for dead lettered messages. Ctrl+C to exit. Channel start consuming. 7.1.2, running the DLX example. Start your RabbitMQ Docker container. Run the DLX consumer, Python DLX consumer pi. This will set up the dead letter exchange and queue. Run the main consumer, Python consumer with looks_by. This will set up the main queue and bind it, configuring the x dead letter exchange argument. Run the producer, Python producer looks_by. This will send 5 messages. Observe the output. Messages task 1, task 2, task 4 will be processed and acknowledged by consumer with looks_by. Messages task 3 and task 5 will be NACKed with requeue equals false by consumer with looks_by, and then instantly picked up and reported by DLX consumer pi. In the RabbitMQ management UI, you'll see messages briefly appear in main queue and then disappear, with the NACKed ones appearing instead in deadalter queue. 7.2 Time to live, TTL. Message expiry. Time to live, TTL, allows you to set an expiration time for messages. If a message is not consumed within its TTL, it will automatically expire and become dead-lettered if a DLX is configured or simply discarded. This is useful for time-sensitive data, where messages become irrelevant after a certain period. TTL can be set in two ways: per message TTL, set when publishing the message using properties expiration. This applies only to that specific message. Per queue TTL, set on the queue itself using the xMessage TTL argument during queueDeclare. This applies to all messages in that queue. If both are set, the smaller, more restrictive TTL value takes precedence. Note that for messages to actually expire and be dead-lettered, they must reach the head of the queue. If there are messages in front of them with long TTLs, or if there's no active consumer, messages will not expire until they are at the front. 7.2.1 Example with TTL. We'll use a simple main queue and configure it with a short TTL, sending expired messages to our existing dead-letter queue. A producer tool pi. This will send a few messages. Import pica, import time, connection equals pica blocking connection, pica.connection parameters, host equals localhost, channel equals connection channel. Declare a normal exchange for our messages. Channel exchange declare exchange equals TTL exchange. Exchange type equals direct, durable equals true. Publish some messages without an immediate consumer. For I in range 3, message equals FTTL message, I+1. Channel basic publish. Exchange equals TTL exchange. Routing key equals TTL task. Body equals message. Hash we could also set per message TTL here. Hash properties equals pica basic properties. Expiration equals 5000, hash 5 seconds. Printf x sent, message. Time sleep, 1, hash give some time for messages to be routed. Print x messages sent. No consumer yet. Connection close. BQ declaration with TTL, declare it occupy. This script focuses on declaring the queue with TTL and DLX. Import pica. Connection equals pica blocking connection, pica.connection parameters, host equals localhost, channel equals connection channel. 1. Declare the dead letter exchange and queue, if not already done by DLX example. DL's exchange name equals deadalter exchange. DLX queue name equals deadalter queue. Channel exchange declare exchange equals DL's exchange name. Exchange type equals fanout, durable equals true. Channel queue declare queue equals DLX queue name, durable equals true. Channel queue bind exchange equals DL's exchange name. Queue equals DLX queue name. Printf declare DLX queue. DLX queue name. 2. Declare the main queue with QTTL and DLX. TTL queue name equals TTL queue. Channel queue declare. Queue equals TTL queue name. Durable equals true. Arguments equals xMessage TTL. 5000 hash messages expire after 5000 ms, 5 seconds. X dead letter exchange, DL's exchange name. Bind TTL queue to TTL exchange. Channel queue bind exchange equals TTL exchange. Queue equals TTL queue name, routing key equals TTL task. Printf declared TTL queue. TTL queue name with TTL 5s, routing to DL's exchange name. Connection close. See DLX consumer pi, reuse from DLX example. This consumer will capture the expired messages. 7.2.2 Running the TTL example. Start your RabbitMQ Docker container. Run the DLX consumer, Python DLX consumer pi. Declare the TTL queue, Python declare it occupy. This sets up TTL queue with its TTL and DLX configuration. Run the producer, Python producer pi. This will send 3 messages, which will sit in TTL queue. Wait for about 5 to 6 seconds. Observe your DLX consumer pi terminal. It should start receiving the messages: TTL message 1, TTL message 2, TTL message 3, as they expire from TTL queue and are moved to deadalter queue. This demonstrates how TTL can automatically clean up old messages, making it useful for caches, temporary data, or user notifications that are only relevant for a short time. 7.3 Policies. Centralized management of queue properties. Setting arguments like xDeadLetterExchange or xMessage TTL during queueDeclare and exchangeDeclare is common. However, manually adding these to every queue declaration in your code can become cumbersome and error-prone, especially across multiple applications or for large deployments. RabbitMQ policies provide a centralized way to define and apply properties to queues and exchanges based on patterns. Policies allow you to define a set of key-value pairs, arguments. Apply them to queues or exchanges matching a regular expression pattern. Control priority if multiple policies apply. This moves configuration details from application code to the RabbitMQ broker itself, making management easier and more consistent. 7.3.1 Setting a policy via Management UI or RabbitMQ. Let's apply a policy that all queues named longtasks should have a dead letter exchange and a specific TTL. Declare the dead letter exchange and queue if not already existing from previous examples. From a terminal, RabbitMQ declare exchange name equals deadalterexchange, type equals fanout durable equals true. RabbitMQ declare queue name equals deadalterqueue durable equals true. RabbitMQ declare binding source equals deadalterexchange destination equals deadalterqueue destination type equals queue. Create a policy via Management UI. Go to http localhost:15672 and log in. Navigate to the Admin tab. Select Policies from the left-hand menu. Click Add/Update Policy. Name: Longtasks Policy. Apply to queues. Pattern longtasks \. This regex will match queues starting with longtasks, followed by anything. Priority: 10. A higher number gives it precedence if multiple policies apply. Definition: add a key dead letter exchange with value deadalterexchange. Add a key message TTL with value 300,000 5 minutes in milliseconds. Click Add/Update Policy. Create a queue without explicit TTL DLX in code. Now, when your application declares a queue like longtasks reporting or longtasks image processing, RabbitMQ will automatically apply the properties defined in the longtasks policy. Example: producer-consumer for policy-applied queue. A. Producer policy QPy. Import Pika. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. Declare a generic exchange. Channel exchange declare. Exchange equals taskmaster exchange. Exchange type equals topic. Durable equals true. Publish message to a routing key that matches our policy pattern, e.g. longtasks report generate. Message generate monthly report. Routing key longtasks report generate. Channel basic publish. Exchange equals taskmaster exchange. Routing key equals routing key. Body equals message. Printf sent message to routing key. Connection close. B. Queue declaration. Consumer or setup script declare policy QPy. Import Pika. Connection equals Pika blocking connection. Pika.connection parameters. Host equals localhost. Channel equals connection channel. Declare the queue that will be affected by the policy. No need to explicitly add xDeadletterExchange or xMessage TTL here. QNametaus equals longtasks report generate queue. Hash matches policy pattern. Channel queue declare, queue equals QNametaus. Durable equals true. Bind the queue to an exchange. Channel queue bind, exchange equals taskmaster exchange. Queue equals QNametaus, routing key equals longtasks report generate. Printf declared queue, QNametaus. Its properties should be managed by policy. Connection close. When you run declare policy QPy and then inspect longtasks report generate queue in the RabbitMQ management UI, you will see its properties, like message TTL and DLX, derived from the longtasks policy, even though they were not asterisk specified in the QDeclare call. 7.4 Summary and what's next. This chapter has equipped you with powerful tools for more sophisticated message management. Dead letter exchanges, DLX. A robust mechanism to capture and reroute messages that are unprocessable, expired, or exceed queue limits, enabling error handling, auditing, and debugging. Time to live, TTL. Allowing messages or queues to expire automatically after a set period, useful for transient data. Policies. A centralized way to apply configuration settings, like TTL or DLX configuration, to queues and exchanges based on naming patterns, reducing boilerplate code and improving consistency. These features, combined with the reliability mechanisms from Chapter 6, acknowledgements, durability, persistence, form a comprehensive toolkit for building resilient and manageable message-driven systems. In the next chapter, we will look at 2 more advanced features that are crucial for ensuring high levels of integrity in your message workflows: publisher confirms and transactions. These features provide even stronger guarantees that messages are indeed received and processed by the RabbitMQ broker itself. Chapter 8: Building Robust Applications. Publisher confirms and transactions. In the journey of building reliable message-driven systems, ensuring a message is processed by a consumer is crucial, which we covered with acknowledgements. But equally important for many applications is guaranteeing that a message actually reaches the RabbitMQ broker after a producer sends it. What if the network connection breaks just after the producer sends a message, but before RabbitMQ acknowledges its receipt? Or what if a sequence of publishing and consuming operations needs to be treated as a single, atomic unit? This chapter introduces 2 powerful features in RabbitMQ that address these concerns: publisher confirms and transactions. These features provide higher levels of integrity and reliability for producers, ensuring messages are not silently lost during the publishing process. 8.1 Publisher confirms, guaranteeing message delivery to the broker. By default, when a producer publishes a message to RabbitMQ, it's a fire-and-forget operation. The producer sends the message and assumes it reaches the broker. However, there's a window of opportunity for message loss. A network issue could prevent the message from reaching the broker, or the broker could crash before it processes the message. Publisher confirms, also known as confirm select, is a protocol extension that allows producers to receive acknowledgements from RabbitMQ for published messages. When publisher confirms are enabled on a channel, every published message is either ACKed, acknowledged positively, or NACKed, acknowledged negatively by the broker. An ACK from the broker means the message has been safely received, processed, and written to disk, if it's a persistent message on a durable queue. A NACK, negative acknowledgement, means the message failed to reach the broker or was not processed correctly by the broker itself. This usually triggers a retry mechanism on the producer's side. There are 3 main ways to implement publisher confirms. Synchronous confirms, simplest. Publish a message, wait for an ACK or NACK before publishing the next. This is straightforward but drastically reduces throughput. Asynchronous confirms, recommended. Register a callback function that is invoked when an ACK or NACK is received. This allows the producer to continue publishing messages without waiting, offering better performance. Batching confirms. Publish a batch of messages, then wait for all confirmations for that batch. Offers a balance between performance and simplicity. We'll focus on asynchronous confirms as they represent the most practical approach for robust, high-performance applications. 8.1.1 Implementing asynchronous publisher confirms. The Pika library, being primarily blocking, requires a slightly different approach for asynchronous confirms, typically implemented with a select connection or an event loop. For simplicity, we'll demonstrate a conceptual approach that illustrates how the confirmation logic would attach to published messages. In a real application, you'd use a non-blocking Pika connection for higher throughput. A. Producer with asynchronous confirms, publish confirms by. Import Pika. Import UUID hash for unique message IDs. Import time. Class publisher confirm producer. Def init self host equals localhost. Self.connection equals none. Self channel equals none. Self host equals host. Self ACKed messages equals. Hash map delivery tag to message for tracking. Self NACKed messages equals. Self message aid equals 0. Def connect self. Print connecting to RabbitMQ. Self.connection equals Pika blocking connection. Pika.connection parameters. Host equals self-host. Self-channel equals self.connection channel. Hash enable publisher confirms on this channel. Self.channel.confirm delivery. Hash register callback for confirms. Self-channel add and return callback. Self-on return callback. Hash for unroutable messages. Self-channel add and deliver information callback. Self-on confirmation callback. Print, connection established and confirms enabled. Def on confirmation callback, self. Method frame, callback for basic hack and basic NACK confirmations. Deliverytag equals method frame dot method dot deliverytag. If method frame dot method dot name equals basic hack. Printf ACK message delivered confirmed. If delivered in self ACKed messages, del self ACKed messages delivered. Elif method frame dot method dot name equals basic knack. Printf knack message delivered not confirmed, republishing or logging error. Hash here you would typically retry publishing or log the error. If delivered not in self naked messages. Self naked messages delivered equals self ACKed messages get delivered. Printf original message body. Self naked messages delivered. Del self ACKed messages delivered. Def on return callback, self, channel, method, properties, body. Callback for basic return, unroutable messages. Printf return message unroutable, routing key, method routing key, body.decode. Hash this means the message reached the exchange, but couldn't be routed to any queue. Hash it's an important signal for dead letter processing or error logging. Def publish message, self, exchange, routing key, message body. Self message aid plus equals 1. Properties equals Pika basic properties. Deliver mode equals Pika spec persistntdlivrimod. Hash make message persistent. Message aid equals str, uid 4. Hash unique ID for tracking. Hash store message body for potential NACK retry. Self ACKed messages self message aid equals message body. Self channel basic publish. Exchange equals exchange. Routing key equals routing key. Body equals message body. Properties equals properties. Hash mandatory equals true ensures basic return callback is triggered if unroutable. Mandatory equals true. Printf x published message message body with delivery tag self message aid. Def close self. If self.connection, self.connection close. Print connection closed. Def main. Producer equals publisher confirm producer. Producer.connect. Hash declare a durable exchange. Producer channel exchange declare. Exchange equals confirm exchange. Exchange type equals direct. Durable equals true. Hash declare a durable queue. Producer channel queue declare. Queue equals confirm queue. Durable equals true. Hash bind queue to exchange. Producer channel queue bind. Exchange equals confirm exchange. Queue equals confirm queue. Routing key equals my key. Hash publish some messages. Producer publish message confirm exchange. Mikey, hello confirmed world 1. Producer publish message confirm exchange. Mikey, hello confirmed world 2. Producer publish message confirm exchange. Other key, this will be unroutable. Hash mandatory will return this. Time sleep 2. Hash give some time for confirms to come back. Print \n pending AC case. Producer racked messages. Print pending NAC case from broker error. Producer naked messages. Producer close. If name equals main. Main. Key parts of publish confirms by self.channel.confirm delivery. This method puts the channel into confirm mode. Once in confirm mode, messages published on this channel will be confirmed. Self-channel add and deliver information callback, self-on confirmation callback. This registers a callback function that Pika will call when a basic hack or basic NAC confirmation is received from the broker. Self-channel add and return callback, self-on return callback. This registers a callback for basic return messages. These happen when a message reaches an exchange but cannot be routed to any queue, e.g., no matching binding. To trigger this, mandatory equals true must be set in basic publish. Without mandatory equals true, unroutable messages are silently dropped by the broker. ACKed messages dictionary, a simple way to track messages by their delivered, which RabbitMQ assigns sequentially per channel until their confirmation is received. Upon ACK or NAC, the message is removed from this dictionary. Running the publisher confirms example. Start your RabbitMQ Docker container. Run the producer, Python publish confirms py. Observe the output. You'll see ACK for the routable messages and return for the unroutable one. Try stopping RabbitMQ immediately after the published messages appear, but before the ACK messages. Without confirms, you wouldn't know if the messages reach the broker. With confirms, the producer would either not receive an ACK after a timeout or receive a NACK, indicating a problem. When to use publisher confirms, when message loss is unacceptable and you need to ensure the broker received your message. Common in financial transactions, order processing, or critical event logging. Trade-offs. publisher confirms introduce a slight overhead due to the back-and-forth communication. Asynchronous confirms mitigate performance impact, but synchronous confirms can significantly reduce throughput. 8.2 Transactions, atomic publish and consume operations, with caveats. RabbitMQ supports AMQP transactions, allowing you to group a series of publish and acknowledgement operations into a single, atomic unit of work. This means either all operations in the transaction succeed or all of them fail and are rolled back. The three methods for AMQP transactions are txSelect, puts the channel into transaction mode, tx.commit, commits the transaction. If successful, all operations are applied. txRollback rolls back the transaction. All operations performed since txSelect are discarded. 8.2.1 Implementing transactions. A. Producer with transactions, producer transaction pi. Import pica. Connection equals pica blocking connection, pica.connection parameters, host equals localhost, channel equals connection channel. Declare a queue. Channel queue declare, queue equals transaction queue, durable equals true. Try. #1, put channel into transaction mode. Channel txSelect. Print channel in transaction mode. #2, publish some messages. Channel basic publish, exchange equals. Routing key equals transaction queue, body equals atomic message 1. Channel basic publish, exchange equals. Routing key equals transaction queue, body equals atomic message 2. Print messages published within transaction, not yet committed. #simulate an error, uncomment to test rollback. #raise value error, simulated error during transaction. #3, commit the transaction. Channel txcommit. Print transaction committed. Messages are now durable in queue. Accept exception as E, printf error, E, rolling back transaction. #4, roll back the transaction on error. Channel tx rollback. Print transaction rolled back, messages discarded. Finally, connection close. B. Consumer with transactions, consumer transaction pi. Import pica. Import time. Connection equals pica blocking connection, pica.connection parameters, host equals localhost. Channel equals connection channel. Channel queue declare, queue equals transaction queue, durable equals true. Channel basicos, prefetch count equals 1. Def callback, ch method properties body. Message content equals body.decode. Print fx received, message content. Try, #start a new transaction for consuming. #note, this is an independent transaction from the publishing one. #it's intended to group a receive plus other DB operations. #CHTX-select. #uncomment to see consumer side transaction. #simulate processing work. Time sleep 1. If bad in message content lower. Raise value error. Simulated bad message will not acknowledge. #acknowledge the message within the transaction. basic hack. Deliveredeg equals method.deliveredeg. Print fx processed and act message content. #CHTX commit. #uncomment to commit consumer side transaction. #print consumer transaction committed. Accept exception as E. Print f error processing message, message content. A. #reject message and potentially put back to queue without commit. basic knack. Deliveredeg equals method.deliveredeg. Requeue equals true. Print message NACK'd and requeued. #CHTX rollback. #uncomment to rollback consumer side transaction. #print consumer transaction rolled back. Channel basic consum, queue equals transaction queue. On message callback equals callback, autoack equals false. Print waiting for transactional messages. To exit press CTRL+C. Channel start consuming. Running the transaction example. Start your RabbitMQ Docker container. Run producer transaction pi. Observe the messages appearing in transaction queue in the management UI only after the commit. If you uncomment the raise value error, they will not appear. Run consumer transaction pi. It will pick up the messages. When to use transactions and their caveats, atomicity. Transactions ensure that a group of publishes or acknowledgements are atomic. For instance, if you publish 3 messages and one fails, all fail. Synchronization. If you perform a tx.commit, all previous publishes acknowledges are synchronized with the broker. Significant caveats of transactions. Performance. Transactions are extremely slow. Each tx.commit or tx rollback is a synchronous network call to the broker, effectively blocking the channel. Throughput is severely impacted. Scope: transactions are channel scoped. If your application crashes while a transaction is in progress, any uncommitted operations will be rolled back. Producer-broker relationship: they only guarantee atomicity between the producer and the broker asterisk. They do not involve consumers. A consumer processing a transactionally published message is a separate operation. Given the performance overhead, AMQP transactions are rarely used in practice for general message publishing. Publisher confirms are almost always the preferred and more performant mechanism for guaranteeing message delivery to the broker. Transactions might be considered for very specific, low-volume scenarios where strict atomicity between a group of publishes is absolutely required, and the performance impact is acceptable. 8.3 Summary and what's next. This chapter introduced you to advanced features for ensuring high integrity in your message workflows. Publisher confirms: the gold standard for guaranteeing that messages successfully reach the RabbitMQ broker, providing much-needed feedback to producers. Asynchronous confirms are generally the most performant approach. Transactions: a mechanism for atomic grouping of publish-acknowledge operations within a single channel. While providing strict atomicity, their severe performance overhead means they are rarely recommended for typical use cases compared to publisher confirms. With a solid understanding of reliability, Chapter 6, and these integrity features, you are well equipped to build production-grade messaging systems. However, designing a reliable message flow is one thing. Deciding how messages fit into your overall application architecture is another. In the next chapter, we will shift gears from RabbitMQ's internal mechanisms to its practical application. We'll explore common use cases, design patterns, and architectural considerations for integrating RabbitMQ into your software systems, offering real-world scenarios and best practices. Chapter 9. Putting it into practice. Common use cases and patterns. So far, we've dissected RabbitMQ's core components, explored various routing mechanisms, and built a safety net with reliability features. Now, it's time to elevate your understanding by considering how RabbitMQ fits into real-world application architectures. This chapter will explore common use cases and design patterns where message queues, and specifically RabbitMQ, provide significant value, illustrating how to leverage its features to solve practical development challenges. 9.1 Deferring CPU-intensive or long-running tasks. Work queues revisited. One of the most classic and widely adopted use cases for a message queue is to offload computationally intensive or time-consuming operations from the main application thread. This ensures that user-facing interactions remain fast and responsive, while background tasks are processed reliably. Scenario: an e-commerce website where users can upload high-resolution product images. Before displaying, images need to be resized, watermarked, optimized, and stored in multiple formats. Performing these tasks synchronously during the upload process would make the user wait indefinitely. RabbitMQ solution. Producer web application. When a user uploads an image, the web application doesn't process it immediately. Instead, it uploads the raw image to temporary storage, e.g., S3 local disk, generates a message containing the image's ID and location, and publishes this message to an image processing tasks queue. It then returns an immediate success response to the user. Consumer image processor worker. A dedicated worker application, or multiple instances of it, consumes messages from the image processing tasks queue. Each worker picks up a message, downloads the image, performs all the necessary transformations, resizing, watermarking, optimizing, uploads the processed images to permanent storage, and then acknowledges the message. Reliability. The image processing tasks queue should be durable, and messages should be persistent. Consumers should use manual acknowledgements and base sickos with prefetchCount equals 1. If an image worker crashes, RabbitMQ redelivers the task to another worker. If a message contains problematic data that causes repeated failures, it can be dead-lettered to an error queue for manual inspection. Benefits. Responsiveness. User experience is improved as image uploads are nearly instantaneous. Scalability. You can scale the number of image processor workers independently of the web server, adding more workers during peak times. Resilience. If workers fail, messages remain in the queue. If storage services are temporarily unavailable, workers can retry or messages can be NACK'd and requeued. 9.2 Decoupling microservices with event-driven architecture, fanout and topic. Modern applications often consist of many small, independent services, microservices, that need to communicate with each other. Direct API calls between these services can create tight coupling, making services dependent on each other's direct availability and prone to cascading failures. Message queues facilitate event-driven architectures, where services communicate indirectly through events. Scenario: an order processing system where placing an order triggers various actions. Updating inventory, sending email confirmations, processing payments, and dispatching shipping requests. RabbitMQ solution: producer order service. When a new order is placed, the order service publishes an order-created event message to an order relevance topic exchange. The message typically contains minimum essential information, e.g., order read. Consumers, inventory, email, payment, shipping services. Inventory service binds its queue to order relevance exchange with binding key order created. Consumes the event to decrement stock. Email service binds its queue to order relevance with binding key order hash or order created. Consumes the event to send a confirmation email. Payment service binds its queue to order relevance with binding key order created. Consumes the event to initiate payment processing. Shipping service might bind to order relevance with binding key order paid, assuming the payment service publishes a new event order paid upon successful payment. Benefits: decoupling. Services don't directly call each other. The order service doesn't know or care how many other services react to an order-created event. This allows independent deployments and technology choices. Resilience. If the email service is temporarily down, the other services continue to function, and valid order-created events for emailing will simply queue up until the email service recovers. Scalability. Each service can scale independently based on its workload. Extensibility. Adding new functionality, e.g., a loyalty point service, simply involves creating a new service and binding its queue to relevant events without modifying existing services. Auditing logging. A separate logging service could bind to or hash on an events exchange to capture all events for auditing or analytics without impacting core business logic. 9.3 Asynchronous notifications and alerts, fanout. Message queues are excellent candidates for sending asynchronous notifications or alerts to multiple subscribers simultaneously. Scenario: a monitoring system needs to send alerts, SMS, email, push notification, Slack message when a server goes down. RabbitMQ solution: producer monitoring agent. When a severity-critical event occurs, the monitoring agent publishes an alert-critical message to a notifications fanout exchange. Consumers, SMS gateway, email sender, push notification service, Slack bot. Each notification service consumes messages from its own queue, which is bound to the notifications fanout exchange. Each gets a copy of the alert critical message and handles its specific delivery mechanism. Benefits: simplicity. A single message publication can trigger multiple delivery mechanisms. Reliability. If a notification service fails, messages queue up until it recovers. Extensibility. Adding a new notification channel, e.g., PagerDuty integration, is as simple as adding a new consumer that binds to the notifications exchange. 9.4 Request response patterns, temporary queues. While message queues are primarily for asynchronous, one-way communication, they can also be adapted for request response patterns, especially between decoupled services where a direct HTTP call might be undesirable. Scenario: a front-end application needs to request a report from a back-end analytics service and receive the report asynchronously. RabbitMQ solution: producer front-end API. Declares a unique, exclusive auto-delete queue, a temporary reply queue with queue equals, to get a unique auto-generated name from RabbitMQ. Publishes a request message to a report request direct exchange with. Correlationed, a unique ID to match request with response. Replito, the name of its temporary reply queue, starts consuming from its temporary reply queue, waiting for a message with the matching correlation ID. Consumer Analytics Service consumes from the report request queue, processes the request. When the report is generated, it takes the Replito queue name from the incoming message's properties and the correlation ID, publishes the report data as a new message to the default exchange or a dedicated reply exchange with the Replito queue name as the routing key and the original correlation ID. Producer, front-end API, continues, receives the response on its temporary queue, compares the correlation ID to its original request to ensure it's matched, processes the report and closes its temporary queue. Benefits, decoupling. The front-end API and analytics service remain independent. Asynchronous handling. The front-end API is not blocked while waiting for the report. Scalability. Multiple instances of the analytics service can process requests concurrently. Caveats. This pattern adds complexity and is generally suitable for asynchronous command query patterns. For immediate, synchronous request response, traditional HTTP APIs are often simpler and more performant. Publisher confirms, Chapter 8, are critical for ensuring the request message reaches the broker. 9.5 Logging and monitoring, fanout or topic. Centralized logging and monitoring systems are essential for understanding application behavior and troubleshooting issues, especially in distributed environments. Scenario: collecting log messages from various application components in a microservices architecture and sending them to different log aggregators, e.g., Elasticsearch, Splunk, or real-time alert systems. RabbitMQ solution: producers application services. Each application service, web server, payment service, database service, logs messages, info, warning, error, debug, and publishes them to a load-events topic exchange. Routing keys could be structured like servicename.level.category, e.g., WebErrorAuth, payment.info transaction. Consumers log aggregators, alert services, Elasticsearch ingester. Binds its queue to load-events with hash to receive all logs and store them. Real-time alerting. Binds a high-priority queue to load-events with error, hash, or critical. Hash to receive only critical errors and push them to a notification service. Auditing service might bind to system, hash to capture all system-level events for compliance. Benefits: centralization, all logs flow through a single point. Filtering, consumers can subscribe only to logs relevant to them. Reliability, logs are buffered in queues, preventing logging systems from being overwhelmed during spikes. Decoupling, logging logic is separate from core application logic. 9.6 Distributed transactions / Saga pattern, topic with callbacks. While AMQP transactions, Chapter 8, are typically not used for complex, multi-service transactions, RabbitMQ can be a critical component in implementing the Saga pattern. A Saga is a sequence of local transactions where each transaction updates data within a single service and publishes an event that triggers the next step in the Saga. If a step fails, compensating transactions are executed to undo prior work. Scenario: a complex order workflow involves payment, inventory reservation, and shipping preparation across separate services. If shipping fails, previous steps must be reversed. RabbitMQ solution: orchestrator coordinator service. This service initiates the Saga and subscribes to events from participating services. Participating services: payment, inventory, shipping. Each service performs its local transaction and then publishes a success or failure event to a topic exchange, e.g., saga.order.payment.completed, saga.order.inventory failed. Event flow: order service initiates, publishes command.payment.process to payment services direct queue. Payment service: processes payment, publishes saga.order.payment.completed or failed to Saga events topic exchange. Orchestrator: consumes saga.order.payment.completed, publishes command.inventory reserve to inventory service. Inventory service: processes, publishes saga.order.inventory.completed or failed. Orchestrator: if inventory failed, publishes command payment refund to payment service. Benefits: eventual consistency, achieves consistency across multiple services without a single, two-phase commit protocol. Resilience. Failures in one step can be gracefully handled with compensating actions. Decoupling. Services remain loosely coupled. Caveats. Saga patterns are complex to implement correctly and debug. They introduce a high degree of asynchronous communication. 9.7 Summary and what's next. This chapter has provided a practical overview of how RabbitMQ can be applied to solve common challenges in modern software development. Work queues for task distribution, event-driven architectures for microservice decoupling, asynchronous notifications for broadcasting alerts, request-response patterns using temporary queues, centralized logging and monitoring, facilitating distributed transactions via the Saga pattern. The power of RabbitMQ lies in its flexibility and robustness, enabling you to build scalable, resilient, and decoupled systems. You've now seen how to use RabbitMQ effectively in various architectural contexts. The next pivotal step is to choose the right client library for your programming language and integrate it with your applications. Chapter 10 will explore how to practically implement producers and consumers in popular programming languages, bridging the gap between RabbitMQ's concepts and your code. Chapter 10, Client Libraries in Action, Examples across languages. By now, you understand RabbitMQ's core concepts, its advanced features for reliability, and common architectural patterns. The bridge between these theoretical constructs and practical application lies in client libraries. These libraries provide the necessary APIs to connect to a RabbitMQ broker, declare exchanges and queues, publish messages, and consume them, all within the context of your chosen programming language. While this book uses Python's Pika library for primary examples, this chapter aims to show you how those same concepts translate to other popular languages. We will demonstrate how to set up basic producer and consumer applications in Node.js, JavaScript, Java, and Go, Golang, highlighting the similarities and minor differences in their approach to interacting with RabbitMQ. Note, for each example, ensure you have the respective language runtime and necessary dependencies installed. We'll use the simplest, most common approach for each, focusing on the core RabbitMQ interaction rather than language-specific best practices, complex error handling, or asynchronous patterns, which would warrant entire books themselves. 10.1 Node.js, JavaScript with AMQlib. AMQlib is a popular, robust AMQP 0-9-1 client for Node.js. It supports both callback-based and promise-based APIs. We'll use promises for a more modern approach. 10.1.1 Setup, AMQlib installation. npm init npm install AMQlib. 10.1.2 Node.js producer, producer.js. This producer will send a simple hello world message to a queue. Const amp equals require AMQlib, async function send. Try, const connection equals await amp.connect, amp//localhost. Const channel equals await connection create channel. Const quename equals hellonodes. Const msg equals hello RabbitMQ from Node.js. Declare the queue as durable. Await channel assert quename durable true. Publish the message to the default exchange, routing to the queue. Persistent, true makes the message persistent. Channel send to quename buffer dot from msg, persistent, true. Console log x sent msg, await channel close, await connection close, catch error. Console error in producer, error message, process exit 1. Send 10.1.3 Node.js consumer, consumer.js. This consumer will receive messages from the queue and print them. It will also demonstrate manual acknowledgement. Const amp equals require AMQlib, async function receive. Try, const connection equals await amp.connect, amp//localhost. Const channel equals await connection create channel. Const quename equals hellonodes. Assert the queue exists durable, true. Await channel assert quename durable, true. Console log waiting for messages in quename. To exit, press Ctrl+C. Set prefetch count for co-s, one unacknowledged message at a time. Channel prefetch 1. Start consuming messages. No ACK, false for manual acknowledgement. Channel.consume, quename, msg equals. If msg equals null, const content equals msg.content to string. Console log x received content, simulate work. Const dots equals content split, length 1, set timeout, equals. Console log x done processing content, channel ACK MSG. Acknowledge the message. Dots 1000, 1 second per dot. No ACK, false, explicitly set no ACK to false. Catch error. Console error, error in consumer, error message, process exit 1. Receive. 10.1.4, running Node.js examples. Start your RabbitMQ Docker container. Run the consumer, Node consumer.js. Run the producer, Node producer.js. Send multiple messages like Node producer.js, task with 1 dot, and Node producer.js, task with 3 dots, and observe the consumer's behavior. 10.2 Java with RabbitMQ Java Client. The RabbitMQ Java Client is the official client library for RabbitMQ. It is widely used in enterprise environments and forms the basis for higher-level frameworks like Spring AMQP. 10.2.1 Setup, Maven POM.xml. Add the following dependency to your POM.xml for Maven project. Dependency. Group IDCOM RabbitMQ /group ID. Artifact IDEM client /artifact ID. Version 5.2.0.0 version. Use the latest stable version. Dependency. Or for Gradle. Implementation COM RabbitMQ client 5.20.0. Use the latest stable version. 10.2.2 Java Producer Direct Producer Java. Import COM RabbitMQ client channel. Import com.rabbitmq.client.connection. Import com.rabbitmq.client.connection factory. Import com RabbitMQ client message properties. For persistent messages, import java.io.io exception. Import java.util.concurrent timeout exception. Public class direct producer. Private final static string QUNAME equals HelloJava. Public static void main string argv throws IO exception timeout exception. Connection factory equals new connection factory. Factory set host local host. Set RabbitMQ host. Try connection equals factory new connection. Channel equals connection create channel. Declare the queue as durable. Channel queue declare, queue name true, false, null. Durable, not exclusive, not auto-delete. String message, hello RabbitMQ from Java. Publish the message, setting it as persistent. Channel basic publish. QUNAME, message properties PRSSDNTTXTPLAIN, message get bytes, UTF-8. System out println, xsent, plus message plus. 10.2.3, Java consumer, direct consumer Java. Import com RabbitMQ client channel. Import com.rabbitmq.client.connection. Import com.rabbitmq.client.connection factory. Import com.rabbitmq.client.deliver callback. Import java.io.io exception. Import java.util.concurrent timeout exception. Public class direct consumer. Private final static string QUNAME equals HelloJava. Public static void main string argv throws IO exception, timeout exception. Connection factory equals new connection factory. Factory set host, localhost, set RabbitMQ host. Connection equals null. Channel equals null. Try. Connection equals factory new connection. Channel equals connection create channel. Declare the queue durable. Channel queue declare, queue name true, false, null. System out println. Waiting for messages from plus QUNAME plus. To exit press CTRL plus C. Set prefetch count for co-s, 1 unacknowledged message at a time. Channel basic costs, 1. Define the callback for message delivery. Deliver callback equals consumer tag delivery. String message equals new string delivery get body. UTF-8. System out println, x received, plus message plus, simulate work. Int dots equals message split, //, length 1 try. Thread sleep dots 1000. 1 second per dot. Catch, interrupted exception ignore. Thread current thread, interrupt, finally. System out println, x done processing, plus message plus. Channel basic ACK delivery get envelope. Get delivery tag, false. Acknowledge the message. Start consuming messages, auto ACK set to false for manual ACK. Channel basic consume, QName, false, deliver callback, consumer tag. False for auto ACK. Catch exception E. System error println, error in consumer, plus eGet message. If channel null and end channel is open. Channel close. If connection null and end connection is open. Connection close. 10.2.4 Running Java examples. Make sure you have Java Development Kit, JDK, installed and configured. Compile the Java files, e.g. javexcp path/to/amp client 5, Roman 20xjar direct producer Java direct consumer Java. Run the consumer. Java cp path/to/amp client 5, Roman 20xjar direct consumer or your IDE's run command. Run the producer, Java cp path/to/amp client 5, Roman 20xjar direct producer. 10.3 Go galling with Stredway/amp. Stredway/amp is a widely used and well-regarded AMQP 0 to 9 to 1 client for Go. Go's native concurrency features, goroutines and channels, make it particularly well-suited for high-performance messaging applications. 10.3.1 Setup, Go modules, Go mod init RabbitMQ. Go get github.com/RabbitMQ/amp 091-Go. 10.3.2 Go producer Go. Package main, import, context, log, time, amp github.com/RabbitMQ/amp 091-Go. Func fail on error, MSG string. If equals nil. Log panic, %s, MSG Func main, con equals amp dial, amp /guest, guest at localhost :5672/. Fail on error, failed to connect to RabbitMQ. Defer con close. Ch, equals con channel. Fail on error, failed to open a channel. Defer ch close. Q chq declare. Hello Go, name. True, durable. False, delete when unused. False, exclusive. False, no wait. Nil, arguments. Fail on error, failed to declare a queue. CTX, cancel equals context with timeout, context background. 5 times second. Defer cancel. Body equals, hello RabbitMQ from Go. Equals ch publish with context, CTX, exchange. Q.name, routing key. False, mandatory. False, immediate. AMQ publishing. Contents type. Text plain. Body, bytes bodies. Delivery mode. AMQ persistent, make message persistent. Fail on error, failed to publish a message. Log print, x sent %as \n, body. 10.3.3 Go consumer Go. Package main. Import. Log. Time. AMP github.com/RabbitMQ/amp 091-Go. Func fail on error, MSG string. If equals nil. Log panic, %s, MSG Func main. Con equals amp dial. Amp /guest, guest at localhost :5672/. Fail on error, failed to connect to RabbitMQ. Defer con close. Ch, equals con channel. Fail on error, failed to open a channel. Defer ch close. Q chq declare. Hello Go, name. True, durable. False, delete when unused. False, exclusive. False, no wait. Nil, arguments. Fail on error, failed to declare a queue. Log print, waiting for messages from %s. To exit press CTRL+C, Q.name. Set prefetch count for co-s, 1 unacknowledged message at a time. Equals chcos. 1 prefetch count. 0 prefetch size. False, global. Fail on error, failed to set co-s. MSGS, equals ch.consume. Q.name, Q. A consumer. False, autoac. False, exclusive. False, no local. False, no wait. Nil, args. Fail on error, failed to register a consumer. Var foreverchan struct. Go func. For d equals range MSGS. Log print x received. %s d body. Assimilate work. Dots equals 0. For char equals range d body. If char equals. Dots ++. Time sleep time duration dots time second 1 second per dot. Log print x done processing. %s d body. Dac false, acknowledge the message. Log print waiting for messages. Press CTRL+C to exit. Forever keep the main Go routine alive. 10.3.4 Running Go examples. Make sure you have Go installed and GOPATH setup. Navigate to the directory containing your producer.go and consumer.go files in your terminal. Run the consumer, go run consumer.go. Run the producer, go run producer.go. 10.4 Common Thread. The AMQP protocol. As you reviewed the code examples across Python, Node.js, Java, and Go, you likely noticed a strong pattern. The specific syntax differs, but the underlying concepts and method calls are remarkably similar. Connecting, all clients need to establish a connection to the broker, usually AMP//host, port. Creating channels. Operations are performed on channels rather than direct connections, e.g., create channel. Declaring queues exchanges. All libraries provide functions to queue_declare and exchange_declare, accepting similar parameters, name, durability, auto-delete, exclusive arguments. Publishing. Basic publish or equivalent send-to-queue, publish with context, takes parameters like exchange, routing key, body, and properties, e.g., persistent delivery mode. Consuming. Basic consume or equivalent consume takes a queue name, a callback function, and acknowledgement settings, auto-ACK, no-ACK. Acknowledgements, basic ACK or equivalent channel ACK, DACK false, is called to confirm message processing. COS, basic COS or equivalent prefetch, COS, is used to control message flow. This consistency comes from all these libraries implementing the AMQP 0 to 9 to 1 protocol. This means that once you understand the AMQP specification and RabbitMQ's interpretation of it, you can largely translate your knowledge to any language with a compliant client. 10.5 Summary and what's next. This chapter has demonstrated the practical application of RabbitMQ concepts in different programming languages. You've seen that despite linguistic differences, the core interaction patterns with RabbitMQ remain consistent thanks to the underlying AMQP protocol. This highlights the portability of your RabbitMQ knowledge across various technology stacks. While you now have the tools to build your message-driven applications, operating RabbitMQ in a production environment requires a different set of skills. In the next chapter, we will shift our focus to the operational aspects of RabbitMQ: monitoring, management, and operational insights. We'll explore how to keep an eye on your broker's health, manage its resources, and glean valuable insights from its activities using its powerful management tools. Chapter 11. Monitoring, Management, and Operational Insights. You've learned how to build robust, reliable message-driven applications using RabbitMQ. Now, it's equally crucial to understand how to operate RabbitMQ effectively in production. This involves continuous monitoring to ensure its health and performance, actively managing its resources, and gaining insights into your messaging system's behavior. A production RabbitMQ instance can become a critical bottleneck if not properly managed, potentially leading to widespread application failures. This chapter will guide you through the essential tools and practices for monitoring, managing, and troubleshooting your RabbitMQ deployments. We'll focus on the built-in RabbitMQ management plugin and briefly touch upon other approaches. 11.1 The RabbitMQ Management Plugin, your control center. As introduced in Chapter 3, the RabbitMQ Management Plugin provides a web-based user interface for administering and monitoring your broker. It's an invaluable tool for both development and production environments. 11.1.1 Accessing the Management UI. Typically, you access it via http://your RabbitMQ host 15672. Remember to secure your management interface in production by changing default credentials and restricting access. 11.1.2 Navigating the dashboard and key metrics. Upon logging in, the Overview dashboard presents a summary of vital metrics: message rates, total messages published, confirmed, delivered, acknowledged, and returned per second. High rates indicate high activity. Spikes can indicate traffic bursts or bottlenecks. Message counts: total messages in queues, messages ready for delivery, and unacknowledged messages. High unacknowledged counts, especially if not due to slow processing, can indicate consumer issues. Connections and channels. Number of active client connections and channels. A sudden drop might indicate network issues or application problems. Nodes, for clustered setups, provides an overview of each node's status, running down, memory usage, and file descriptor usage. Key tabs for operational insights. Connections, purpose, view details of active client connections. Insights, identify misbehaving clients, e.g., those holding open too many connections, verify expected application connections, understand network latency. Actions, close errant connections. Channels, purpose, view active channels, which are the logical communication pathways over a connection. Insights, monitor prefetch limits, unact message counts per channel. High unact messages on a channel for a long time might mean a consumer is stuck or crashed without cleanly closing its channel. Actions, close stale channels. Exchanges, purpose. Inspect all declared exchanges, their types and properties. Insights, verify correct exchange types, direct, fanout, topic, and durability. Check message rates through specific exchanges. Actions, declare new exchanges, though usually done programmatically, delete unused ones. Queues, purpose, the most frequently used tab for monitoring the backlog. Insights, ready messages, messages waiting to be delivered to consumers. A continuously growing number indicates consumers are too slow, too few, or have stopped processing. Unacknowledged messages, messages sent to consumers but not yet acknowledged. A high number signifies slow processing, consumer crashes, or a prefetch count that is too high. Consumers, number of active consumers on the queue. If it's 0 or less than expected when messages are ready, consumers might be down. Message rates, incoming outgoing rates for the queue. Memory, memory consumed by the queue, messages, and metadata. Actions, publish message, send test messages directly to the queue, implicitly via default exchange. Get messages, manually pull messages for inspection or debugging. Purge, delete all messages in the queue, use with extreme caution in production. Delete, remove the queue entirely. Admin, purpose, manage users, virtual hosts, and policies. Insights, audit user permissions, manage virtual host isolation. Actions, create delete users, change passwords, create update virtual hosts, define policies for queues exchanges. 11.1.3, tracing and message flows. The management plugin also offers tracing. Under the admin tab, you can enable a tracer. This can log all AMQP protocol traffic to a file, which is invaluable for debugging complex routing issues or unexpected message drops. Caution, can generate very large files and incur performance overhead if left on too long in production. Visualizer, Federation shovel alarms. For more advanced setups, it can provide visual representations of your messaging topology. 11.2 Command line tools, RabbitMQ and RabbitMQ. For automation, scripting, and server-side management, RabbitMQ and RabbitMQ are indispensable. 11.2.1 RabbitMQ. This is the primary command line tool for managing a RabbitMQ server directly. It requires direct shell access to the server where RabbitMQ is running. Common RabbitMQ commands. RabbitMQ status provides general broker status, including uptime, memory usage, running applications, and listener ports. RabbitMQ lists queues name, messages, consumers. Lists configured queues with their properties and current state. You can specify columns to display. RabbitMQ list queues name, message ready, message unacknowledged, consumers, idle since already timestamp. RabbitMQ list exchanges. Lists all exchanges. RabbitMQ list connections, lists all open connections. RabbitMQ list channels, lists all open channels. RabbitMQ list users, lists all users. RabbitMQ adducer username password, adds a new user. RabbitMQ setuser tags username tag, sets tags, e.g., administrator. RabbitMQ set permissions p vhost username conf write read, sets user permissions for a virtual host. RabbitMQ close connection name reason, forcefully closes a connection. RabbitMQ stop app, RabbitMQ start app. Stop start RabbitMQ applications without affecting the Erlang VM. RabbitMQ stop, RabbitMQ start. Stop start the entire RabbitMQ server process. 11.2.2 RabbitMQ. This is a Python-based command line tool that wraps the RabbitMQ management API. It's more user-friendly for most management tasks than RabbitMQ, as it interacts with the HTTP API, allowing you to manage remote RabbitMQ instances easily, assuming management plugin is enabled and accessible. You can download RabbitMQ directly from your broker's management URL, e.g., http localhost:15672/cli/RabbitMQ. Common RabbitMQ commands. RabbitMQ host user p password list queues, lists queues. RabbitMQ declare queue name equals -q durable equals true, declares a durable queue. RabbitMQ declare exchange name equals myExchange type equals direct, declares an exchange. RabbitMQ declare binding source equals myExchange destination equals myQ routing key equals mykey, declares a binding. RabbitMQ publish exchange equals myExchange routing key equals mykey payload equals hello from CLI, publishes a message. RabbitMQ get queue equals myQ, retrieves messages from a queue. RabbitMQ purge queue name equals myQ, purges messages from a queue. RabbitMQ list connections, lists connections. RabbitMQ is especially powerful for scripting and automating RabbitMQ setup and teardown for testing or deployment. 11.3 External Monitoring Solutions. While the management plugin provides a good overview, for production systems, you'll typically integrate RabbitMQ metrics into your existing monitoring stack, e.g., Prometheus, Grafana, Datadog, Elk Stack. Prometheus Exporter. RabbitMQ provides a Prometheus and Grafana integration. Metrics are exposed via a dedicated endpoint, allowing Prometheus to scrape them. Grafana dashboards can then visualize these metrics, providing live views of queue backlogs, message rates, connection counts, and more. This is highly recommended for continuous monitoring and alerting. Logs. RabbitMQ generates logs that contain important information about connections, channel errors, startup shutdown events, and internal issues. Ensure these logs are collected centrally, e.g., by a logging agent, and sent to your log management system for analysis and alerting. OS-level monitoring. Monitor the underlying server's CPU, memory, disk I/O, and network usage. RabbitMQ is an I/O-intensive application, and insufficient resources can lead to significant performance bottlenecks. 11.4 Common operational scenarios and troubleshooting tips. Growing queue backlogs. Symptom: message-ready count is continuously increasing in the management UI. Cause: consumers are too slow, stuck, crashed, or there aren't enough of them to handle the message load. Action: check consumer application logs, scale up consumer instances, optimize consumer processing code, check prefetch count. High unacknowledged messages. Symptom: message unacknowledged count is high. Cause: consumers are processing messages slowly, got stuck, or crashed without sending acknowledgements. Action: diagnose consumer issues. If a consumer is stuck, restarting it might requeue the unacknowledged messages. Review prefetch count settings. Often an overly high prefetch count can exacerbate this problem during consumer failures. Broker crashing restarting. Symptom: RabbitMQ service is down. Cause: resource exhaustion, memory, file descriptors, internal Erlang VM error, misconfiguration, disk full. Action: check RabbitMQ logs immediately for crash reports or warnings. Check OS-level metrics for resource exhaustion. Ensure queues and messages are durable persistent for data recovery. Client connection failures. Symptom: applications unable to connect to RabbitMQ. Cause: RabbitMQ not running, firewall issues, incorrect host port in client, too many open connections, file descriptors on broker limiting new connections. Action: use RabbitMQ status to confirm broker is running. Check firewall rules, review connection limits. Disk alarms. Symptom: RabbitMQ producers are blocked, logs show disk alarm or memory alarm. Cause: the disk where RabbitMQ persists messages is full or nearly full. RabbitMQ blocks producers to prevent data loss. Action: clear disk space. Address the root cause, e.g., persistent messages accumulating in queues, fast producers overwhelming slow consumers. Unroutable messages. Symptom: messages published with mandatory equals true are returned, triggering basic return callback. Cause: messages reached an exchange but had no matching queue binding. Action: check publishing applications routing keys. Verify exchange type and queue bindings. Implement logic in the producer to handle returned messages, e.g., dead lettering, logging, alerting. 11.5 Summary and what's next. Operating RabbitMQ effectively is as important as developing with it. The RabbitMQ management plugin provides a vital graphical interface, while RabbitMQ and RabbitMQ offer powerful command line capabilities for automation. Integrating with external monitoring solutions ensures continuous visibility and proactive alerting for potential issues. By understanding common operational scenarios and troubleshooting techniques, you can ensure your messaging infrastructure remains healthy and responsive. This chapter concludes our deep dive into RabbitMQ's features and their practical application. In the final chapter, we'll expand our perspective to broader deployment and scaling strategies, culminating in a set of best practices for using RabbitMQ in production environments. Chapter 12. Deployment, Scaling, and Best Practices for Production. You've mastered RabbitMQ's concepts, built reliable applications, and learned how to monitor its health. The final piece of the puzzle is deploying RabbitMQ to production environments, ensuring it can handle required loads, scale effectively, and operate reliably around the clock. This chapter covers the critical considerations for production deployments, including different scaling options and a consolidated list of best practices that will serve you well in the real world. 12.1 Deployment Strategies. Single node versus clustering. The first decision in deploying RabbitMQ is choosing your topology. 12.1.1 Single node deployment. Description: a single RabbitMQ server instance. Pros: simplest to set up and manage, lowest resource consumption. Cons: single point of failure. If the server goes down, RabbitMQ is unavailable. Limited scalability for very high throughput or large queue backlogs. Use cases: development, testing, small applications, non-critical services where brief downtime is acceptable. Recommendation: avoid for production systems requiring high availability and resilience. 12.1.2 RabbitMQ clustering. Description: multiple RabbitMQ nodes logically grouped together to form a single broker. They share users, virtual hosts, exchanges, and bindings. Key concepts: node types. RabbitMQ nodes can be disk nodes, store data to disk, most common, or RAM nodes, store only volatile data in memory for performance, less common. Most production deployments use all disk nodes for durability. Queue types: classic queues, the default queue type. Messages in a classic queue can physically reside on only one node. If that node fails, the queue becomes unavailable until the node recovers. Mirrored queues, classic, a mechanism to replicate classic queues across multiple nodes. Messages published to a mirrored queue are replicated to all mirrors. If the master node, where the queue physically resides, fails, one of the mirrors takes over as the new master, providing high availability for the queue's data. This is achieved via policies. Quorum queues. Introduced in RabbitMQ 3.8, recommended for new deployments. A modern queue type based on Raft consensus algorithm, designed for distributed and highly consistent queues. Messages are automatically replicated across a majority, quorum of nodes. They offer stronger consistency guarantees, at least once delivery semantics even in failure scenarios, and are simpler to configure for high availability than mirrored classic queues. Pros: provides high availability, HA, and increased throughput capacity by distributing load across nodes. Cons: more complex to set up, manage, and scale. Requires careful consideration of network latency between nodes. Cluster needs an odd number of nodes for quorum, e.g., 3 or 5 for robustness. Use cases: most production applications where high availability and fault tolerance are critical. 12.1.3 Federation and Shovel plugins. While clustering is for tightly coupled high availability, Federation and Shovel are for looser, geographically distributed messaging infrastructures. Federation connects exchanges and queues across different brokers, even geographically distant ones. Useful for very distributed systems or bridging different RabbitMQ clusters without full clustering. Shovel moves messages reliably from a source queue exchange to a destination queue exchange, potentially on a different broker. can be used for reliable data transfer between clusters or for offloading messages from a busy cluster. 12.2 Scaling RabbitMQ. Scaling RabbitMQ goes beyond simply adding more nodes to a cluster. 12.2.1 Horizontal scaling, adding more nodes. Cluster nodes, add more nodes to an existing cluster. Distribute CPU, memory, and network load. With quorum queues, data is replicated across these nodes. Load balancers. Place a load balancer, e.g., HA proxy, cloud load balancers, in front of your RabbitMQ cluster. Clients connect to the load balancer, which distributes connections among the healthy cluster nodes. 12.2.2 Vertical scaling, upgrading hardware. More RAM, messages in memory are processed faster. Even with persistence, RabbitMQ uses memory for caching and metadata. Faster CPUs, for routing messages and handling TLS connections. Faster disks, SSDs/NVMe. Crucial for durable queues and persistent messages, as disk I/O often becomes the bottleneck in busy systems. Dedicated storage is typically preferred over network file systems. Network bandwidth. High message rates will consume significant network bandwidth between clients and the broker, and within the cluster, for replication. 12.2.3 Application-level scaling. Often, the bottleneck isn't RabbitMQ itself, but how applications interact with it. More consumers. The easiest way to scale message processing is to add more consumer instances. With work queues, Chapter 4, RabbitMQ automatically distributes load. Optimized consumer logic. Ensure consumers process messages quickly and efficiently. Slow consumers create backlogs. Connection and channel management. Reuse connections. Creating new connections is expensive. Reuse long-lived connections for multiple operations. One channel per thread process, or carefully manage. Channels are lightweight, but using one per concurrent operation, or thread/coroutine, prevents blocking. Connection pooling. Utilize client-side connection pooling where available. 12.3 Essential best practices for production. 12.3.1 Security. User management. Never use the default guest user in production. Create specific users for applications with minimal necessary permissions for their virtual host. Virtual hosts. Use separate virtual hosts for different applications or teams for isolation and permission management. TLS SSL. Encrypt client-to-broker and internode communication using TLS SSL. Firewall rules. Restrict access to RabbitMQ ports, 5672 for AMQP, 15672 for Management UI, to only trusted IPs/networks. Audit permissions. Regularly review user permissions to ensure principle of least privilege. 12.3.2 Reliability and durability. Durable queues and persistent messages. For critical messages, always declare queues as durable and publish messages with delivery mode equals to persistent. Publisher confirms. Enable publisher confirms on producer channels to guarantee messages reach the broker. Implement retry logic for NACK'd or returned messages. Manual acknowledgements. Always use manual acknowledgements. AutoACK equals false on consumers for critical messages. Implement proper error handling and basic hack or basic NACK based on processing success. Co-S prefetch count. Set appropriate prefetch count on consumers, typically 1, to ensure fair dispatch and prevent consumers from overwhelming themselves or hoarding messages. Dead letter exchanges, DLX. Configure DLXs for critical queues to capture unprocessable, expired, or rejected messages, preventing data loss and enabling debugging. Time to live, TTL. Use TTL for time-sensitive data that should expire or be dead-lettered if not processed within a defined period. 12.3.3 Monitoring and alerting. Comprehensive monitoring. Don't just monitor message rates. Track queue sizes, ready and unacknowledged messages, consumer counts, connection counts, memory usage, disk utilization, and CPU. Alerting. Set up alerts for critical metrics such as queue backlog exceeding a threshold, 0 active consumers on a key queue, disk or memory alarms, RabbitMQ will block producers. Significant drops in message rates, producer issue, or delivery rates, consumer issue. No downtime in a cluster. Log management. Centralize RabbitMQ logs in a log management system for easier analysis and debugging. 12.3.4 Configuration and Optimization. Resource limits. Ensure the server running RabbitMQ has sufficient RAM, CPU, and fast disk I/O. Configure appropriate file descriptor limits for the Erlang VM. Memory and disk alarms. Understand and configure VM memory high watermark and disk free limit to prevent the broker from running out of resources. Queue declaration. Declare queues and exchanges on both producer and consumer sides. Declare is idempotent to ensure topology exists proactively. Avoid unnecessary operations. Don't delete and recreate queues exchanges frequently if they are long-lived. Don't fetch messages for inspection using basic get in production code if basic consume is appropriate. Client connection reuse. Establish long-lived connections from applications to RabbitMQ. Reusing connections and channels is far more efficient than creating new ones for every message. Queue length limits. For some types of queues, consider setting Xmax length to prevent unbounded queue growth that could exhaust disk space. Messages exceeding this limit will be removed and dead-lettered if DLX configured. 12.3.5 Operational preparedness. Regular backups. Backup RabbitMQ definitions, users, vhosts, exchanges, queues, bindings, policies. While messages themselves are usually ephemeral or can be redelivered, the definitions are critical. Disaster recovery plan. Understand how to recover your RabbitMQ instances from a major outage. Upgrade strategy. Plan for version upgrades, which might involve downtime or rolling upgrades in a cluster. Test upgrades in staging environments first. 12.4 Conclusion. Building your message-driven future. Congratulations! You've journeyed from the fundamental concepts of message queues to advanced RabbitMQ features, common architectural patterns, and crucial operational best practices. You now possess a comprehensive understanding of RabbitMQ for developers and are equipped to design, implement, and manage robust message-driven systems. RabbitMQ is a versatile and powerful tool, but like any distributed system component, it requires careful consideration. Embrace its asynchronous nature, leverage its reliability mechanisms, and apply the best practices outlined in this book. This approach will allow you to build applications that are more scalable, more resilient, and ultimately, more capable of meeting the demands of modern software. The world of distributed systems is constantly evolving, but the core principles of decoupling, fault tolerance, and efficient communication remain timeless. RabbitMQ provides a solid foundation for these principles, empowering you to build the next generation of robust and responsive applications. Happy coding, and may your messages always find their way.